Okay, guys, it's time we start our session today. I've started the recording. We normally do the recording of these sessions because some of our colleagues in the group or in our community are not able to join the session. So we normally do the recording so that we can share the recording of the session and they should be able to review it later. Again, thank you so much for joining our today's session. This is a platform where we share knowledge and empower each other as network engineers. We've been having these sessions for almost 2 years right now. We started with Hyperion last year, and then this year we are doing the network engineering 101 sessions where we invite engineers from different domains to come and share their knowledge. Again, you don't have to be an expert. You just need to have something to share with the rest of the community, and then you can come in and share your knowledge with the rest of the team. This is session 7. In session 6, which was last weekend, we did discuss about MPLS principles, the working principles, the theory of MPLS, how it works, and different solutions, different options that you have as a network engineer when you are managing a network that is configured with MPLS, the benefits of MPLS, and all those details to do with MPLS. Now, when you just cover theory alone, you may not really appreciate and understand MPLS as a protocol. You need to go ahead and do some simulations. You need to do the labs because at the end of the day, you will be configuring this protocol on your network. So you need to understand how you will configure this MPLS, whether it's in L3 VPN or L2 VPN. You also need to understand how you will troubleshoot and verify these services on your network. That's why we have planned to have these back-to-back sessions for MPLS so that you not only just understand the theory, but you also understand how to implement MPLS protocol on your networks. So today we have David coming back again with MPLS Lab to help us understand how to configure and troubleshoot MPLS on networks. Some rules before I bring in David. Just ensure that you keep your mic muted to avoid any distractions. If you have any question, you can raise up your hand. And then David will be taking breaks and taking your questions because we don't want questions to be disrupting all the times. So he will have sections where he will request us to ask questions and then he will respond so that we have a smooth flow of the session. So thank you so much for joining the session again, and I hope we will have a very interactive session today. Feel free to again ask your questions whenever you have an opportunity. You can also send your questions on the chat and we will be picking them and responding to them. So let's enjoy the session. Just confirm you are able to hear the audio and also you are able to see the screen that is shared by David. You can just give us thumbs up and then I'll invite David to come in and take us through this MPLS lab session. Okay, David, you can come in and take it over.
Okay, thank you, Martin. Good morning, good afternoon, good evening from wherever you're joining us from. If this is the first time you're joining us, my name is David Witter. I'm a network engineer. And today we're just going to do a continuation of what we had last week. Last weekend we had a theory on MPLS. We had a very good session. So today we're going to do the lab, building on the theory that we learned and getting our hands quote unquote dirty with the lab. So today there'll be no theory. We're just going to do the lab, which is a practical session. Now, Martin has already given you the rules of engagement, but if you really have a burning question in the middle of my presentation, you are free to ask. But if it's not really burning, we'll have a Q&A session at the end of this recording this session. My goal is to ensure we are doing this the configurations under 2 hours, so that we can have enough time, to go through the questions that people might have. I'm very aware that we have we have the beginners, we have intermediate and expert engineers on the call. So I'm going to do my best, especially to make sure that the beginners and intermediate engineers on the call understand how MPLS works. So this is what we'll cover today. If you can see my screen, it might look like a lot of items to cover, but I can assure you it's not really a lot. I just broke them down for easy understanding. So we will have to configure IP reachability in our MPLS service provider core. Then assign it. So we have to assign IP addresses to all the relevant interfaces. And in the interest of time, I've already gone ahead and configured IP addresses. I've configured loopbacks. Okay. And then the loopback IPs will correspond to the device number, as we'll be seeing in a few. I have gone ahead and configured an IDP, because for MPLS to work, we need an IDP, basically reachability within your MPLS core, and the preferred IDPs for MPLS is ISIS and OSPF. So for this lab, I've chosen to go with ISIS. So I have configured ISIS on all the devices that are participating in the MPLS except 2, so that we can configure those ones together from scratch. So this is what has been done. So number 2 all the way to number 9 is what we will be configuring. Now, after I hope, if you want to take a screenshot of these items, you can do it before we move on. But basically, this is what we're going to cover today. And before we start, I will have to explain the topology. So I believe everyone has taken a screenshot if they want to, but it will be here for us to refer to. So let's go back. Let's go quickly to the lab. I'm not sure I can't show that. Okay, what is happening? Just give me a second. Technology is failing me here.
David, there is some background from your end, background noise from your end. I don't know whether...
I'm not sure I have any control over that, Martin, because where I am, it's close to the road, so okay. I might not have control over that, unfortunately. So I apologize in advance. So is my screen visible? Everyone can see my screen?
Yes.
All right, perfect. Okay. So now here we are. Allow me to take about 10 minutes or less to just explain what's happening on the screen that you are seeing, or 10 minutes or less. So at the middle here, this is where we have our MPLS core. I've decided to give it a name that you are familiar with. The name here is LIFE, MPLS backbone. Now, in terms of the lab, we're going to use Huawei and Cisco devices. Okay. So the devices that you see with this icon here, this device here, that device, and that device, those are Huawei NE platforms. So that's Huawei. Down here, or in the middle here, I've used Cisco device, but it's Cisco IOS XR. This is the icon that I've chosen to go with. So Cisco IOS XR, and then Up here we have the EvenG built-in virtual PCs. So we have a virtual PC here, we have another virtual PC here, and then this is also another virtual PC, but I have given it an icon of a server because we want to depict, or for lack of a better word, pretend that we have a server this side, but we'll have to access it. Okay. Now the rest of the devices that I have not mapped, are Cisco IOS XZ. So this is let me use a different pen. So this is Cisco IOS XZ, another IOS XZ, another IOS XZ, IOS XZ, this one here, and this one here. Okay, so I hope we are clear there before I proceed. Now, when it comes to device names, so we are pretending that Lifey MPLS backbone as a service provider, Lifey Technologies as a service provider, has operations in Africa. I was biased because, as you may know, I'm an African, but that doesn't mean I don't like people who are not Africans. So guys who are outside of Africa, it's just purely for the purposes of this lab. So nothing personal. Now, I have decided to give them, if you concentrate on our MPLS backbone with the color peach, this color is peach. My wife tells me this is peach color. I don't know how it looks on your end, but I was told this is peach color. So the devices here, I've given them names that we can relate to. So RW means Rwanda, and this is our PE device that connects to the customers. And then UG means Uganda, TZ means Tanzania, and KE means Kenya, then ZA means South Africa. Okay, so in terms of L3 VPN, before I go there, let me explain the IP addressing. So the IP addressing, as Lifey Technologies, we've been assigned this particular block, that is 20.1.0.0/16. If you guys attended EV's first class about subnetting, then we went to Afrinic and they gave us this particular block. If this particular block belongs to the company you're working for in real life, again, I apologize. This is purely for the lab purposes. So please do not sue me. So this particular block here has been subnetted to give us /24s. It has been subnetted to give us /24s. Now, in terms of addressing schema, the device here is 1, device name number here is 2. So therefore, we've taken the third octet to be 12. Up here, this device here is 2. This device here is number 3. So the third octet is 23. And therefore, this interface, for example, will be 20.1.23.2. This particular interface here will be .3. Down here, this particular interface will be .1. This here will be .4. So I've decided to use /24s just for simplicity and so that everybody can understand what we're doing. But in real life scenario, you will not be wasting IP addresses like this. That's why down here, where we have a peering between these two devices, I have decided to go with a /31, which is what you'll find configured in most service provider or enterprise networks. So yeah, I know people will ask me why /24, but I've just explained it to you for simplicity. But in real life scenario, you not waste IP addresses like this. You will have to conserve them. As we know, IPv4 addresses have been exhausted in some regions, and therefore we need to be very careful on how we use them. Now, after that, the color green on my left and on my right, which is basically also your left and right. Now this one here will be our L3 VPN customer. So we are pretending that we have the customer AS100 has operations in Rwanda, and they have to access their branch or other customer, sorry, their branch or their offices in South Africa. That's why we have a server here, which we'll have to configure so that all the customers in Rwanda, for this particular, all the devices or the users in Rwanda for this particular customer will have to access our server in South Africa. Now down here, we're going to configure L2 VPN, but not the legacy configuration whereby you just configure L2 VPN for a customer in Rwanda and then for another customer in South Africa, and it sort of become a very big switch. The service provider becomes a very big switch, so it appears as if they are connected via switch at layer 2. What we're going to do here, we are going to this customer has come to us as 670. They have come to us as Lifey Technologies, and then they have told us for some reasons. It could be because of financial constraint or for whatever reasons the customer may be having. They have come to us and told us that they would want to get content from Microsoft, that is Facebook, that is Meta, and then Google. So these particular upstream providers here are in South Africa. As you can see, they are connecting to our device. I've used the same color just as you know that this here is an extension of this particular infrastructure. So we're in South Africa. Now, we, as Lifey Technologies, we have a pairing between Google and Meta. Okay, I know this is an MPLS, but MPLS Lab, but I want to show you how we can use L2 VPN to enable this customer here, ABC, to be able to do to pair with us in South Africa, and by doing that, this is via BGP. Specifically, we're going to do IPv4, not IPv6, for simplicity. So they'll be able to pair with us here in South Africa, and if they do pair with us, then it means the content that Meta and Google are giving us will be able to give this customer. That is the main goal for this customer, and that's why we'll have to do the L2 VPN configuration in this way. But down here, I decided to just come up with a topology. We're not going to configure this, but this is normally what happens. You have your service provider network here, okay, and then now the customer connects to you in Rwanda, that is CE04, and then connects to you in South Africa, that is CE05. So what we basically do is that we configure IP address here, and then we configure IP address here. And the L2 VPN I'm talking about here is the virtual private wired services, which basically involves connectivity between only two devices. The other flavor of L2 VPN, which is virtual private LAN services, you might have multiple other devices connected here. For example, you can have a C06 here. So this acts as a branch, and then this is HQ. This can act as HQ, and then this one here will act as a branch, another branch. So this is VPLS. But for us today, we're going to purely deal with virtual private wired services, which is connectivity between only two customer devices, not more. And we are doing that going through the service provider infrastructure, because we don't have an infrastructure of our own, so we have to rely on our service provider to give us that. Now, so this is what I wanted to just show you here. We can go ahead and remove it, but just to a quick thing to note about virtual private wired services, that is L2 VPN flavor. The subnet has to be the same on either side for connectivity, because basically what this service provider infrastructure gives us is what is equivalent to this. You have a CE device here, and then you have the service provider network here, and then we have another CE device here. So to the customer, this appears like a switch. it's transparent to the customer. Therefore, the connectivity here is as if they are connected point to point, but really they're going through our service provider network here. Okay, so this particular subnet should be the same. That's why we are using 172.16.45.0/24, and then on this other side, it's also the same subnet. That is the requirement of L2 VPN, specifically for this particular one, virtual private wired services. Now, we've taken some time to discuss about what this topology looks like, why this topology, and what our requirement is. So our requirement is this particular users in Rwanda, they are connected to Rwanda, they should be able to access services from this server. Maybe they have a mail server here, or maybe they have any services that they want to access in South Africa. Then they have to access it via our service provider environment instead of using the internet. Let me mention this, that we are not giving the customer here for L3 VPN, the customer in green, we're not giving them internet. No, we are enabling them to be able to access their own services that are located at a different geographical location from them. That is one of the most important or key advantages of using an MPLS network, because it gives you a virtual private network for you to be able to access your services that might be geographically distant from you. And then for the case of our company, the company here that is called ABC, that has come to us as Lifey Technologies, for them, they will be able to use our MPLS infrastructure to be able to get content from this particular two upstream providers in South Africa. Okay, so that is exactly what we're going to do. And if there are no any questions about the topology, I would like just to begin the configuration. Any questions? Okay, I take it silence means everything is fine.
There was a question on the chat. Ilunga was asking why you chose to use ISIS instead of OSPF in your setup.
Ilunga, I'll give you a very straight answer. It's because, okay, there are so many other benefits, but for this particular one, ISIS is actually very scalable compared to OSPF when you're dealing with a very large network. So that's why I've chosen to go with ISIS. It's purely because of scalability. Okay, thank you. Now again, confirm you can see my screens very well. That font is very okay. I think it's fine. Now, as I mentioned to you that we've gone ahead and configured IP addresses. So all these devices here have IP addresses. All of them, they have IP addresses. Now, for ISIS, this device here is not configured with ISIS. So Rwanda PE01 is not configured with ISIS. Okay. And South Africa PE05, which is another provider edge. If you remember our theory, the device that is connecting to customers, which is our device in our MPLS infrastructure, is a PE device. And then the devices that are not connecting to customers, they only connect to themselves, and PE devices within our infrastructure are called P, provider devices, or another name that we gave them. If you can remember, we gave them a name called label switch router. So this one is a label switch router, label switch router, label switch router. And then for the PEs, we gave them a name called LER, label edge router. It can be ingress or egress depending on where traffic is flowing from. So we have configured ISIS here. We have configured ISIS here on the Cisco ISXR, and we have configured ISIS on this particular Huawei device. So this device here and this device here do not have ISIS. So that's what we will configure. And then from there now, MPLS is not at all configured within our MPLS, within our infrastructure. That's what we'll also have to configure. So the reason as to why we need an AIGP is because this device should learn all the routes, all the prefixes within our infrastructure as LiFi technologies. And then after that, after it has learned, all the prefixes, the importance is because later on we'll have to transport prefix customer routes from Rwanda all the way to South Africa. And how we'll do that, we'll leverage the use of I think I gave it here. We leverage the use of what we call the MPBGP, that is multi-protocol border gateway protocol, multi-protocol border gateway protocol, which will actually enable us to be able to transport routes from CE09 all the way to CE08 so that there can be connectivity. Now, that particular MPBGP configuration only happens, if you remember, only happens between provider edge routers. Remember, the other name for MPLS MPLS cloud or MPLS backbone could be according to other literature, it could also be called an MPLS BGP FreeCo. It also referred to as BGP FreeCo. That's because the provider devices, the provider routers, this one here, this one here, and this one here, do not participate in any BGP configurations. The only place we configure BGP is between the only place we configure BGP is between provider edge devices which are connecting to the customer. That's where we now will have to configure MP BGP. That's why we need reachability, because and this MP BGP is configured using loopbacks for stability, not physical interfaces. Because if this interface were to go down and we've configured whatever, for example, if we're doing BGP, if you configure, actually, first of all, it's not even possible to use physical interfaces to connect between PEs unless they're directly connected to each other. But if they're, for example, this PE, for example, our PE here is in Rwanda, the other PE here is in South Africa. So there's no direct connection between these devices, but because ISIS is configured, now the Rwanda device and the device in South Africa, they can be able to learn routes, including loopback IP addresses of each other, and therefore form an internal BGP peering, specifically VPN v4, because that's what will allow us to configure. We're not going to configure the normal BGP. No, that's what is done on a normal environment. But within the MPLS infrastructure, we only configure VPN v4 or VPN v6 if you're using IPv6. Now, this particular peering here is already configured and up and running, because we're not doing here. We are just doing normal BGP, specifically eBGP. So BGP is not a topic of discussion today. So I have gone ahead and configured BGP peering here so that they are able to exchange routes. That's what is pre-configured. So without much talk, let's get into it. So we start with Rwanda PE. We go to Rwanda PE 01. As you can see, if you this is Huawei. If you remember the icon, I said these are the four dark blue ones are Cisco. Sorry, Huawei. So if you display ISIS, display current configuration ISIS, we don't have it configured. If you go to South Africa PE05 and then show run section router ISIS, we don't have it configured. The only place we have configured ISIS is in Uganda, and we're actually getting routes. So if you show run section ISIS, we've configured ISIS in Uganda, and then we've gone ahead and configured ISIS in Tanzania. That is the Cisco ISXR. This is how if you show run router ISIS, This is how ISIS, so we've configured ISIS in that device also, and we can actually confirm if we're getting routes. So we are getting routes from Uganda, that is the loopback interface of Uganda. We're also getting the loopback interface of Kenya P03, and then we are also getting this physical interfaces. Okay, so as you can see, we're not getting the loopback interface of Rwanda, that is 111, and then for South Africa it's 5555 as the loopback interface. But as now we're going to configure ISIS so to have reachability before configuring MPLS. So let's go to Rwanda. First of all, let's confirm that we have IP addresses. So this display IP interface, and then we have to exclude L3 VPN and those ones that are down. I think that one has failed me terribly. Let me just display IP interface brief, exclude L3 VPN, and then exclude interfaces that are down. So we have IP addresses configured. So this device, this interface facing Uganda, this interface facing Tanzania is configured. Let's go ahead and configure SIS. So how we configure SIS, I know Theophilus will come back and give us a lab on that, but how we configure SIS in Huawei and Cisco are slightly different, but the idea is the same. So we just say SIS. If you don't give it any process ID, it will automatically assign one. So let's just do one. Now, what we need here, we need a network entity ID. So we do a network entity ID in this format. So since this is P01, we're going to use one to to distinguish it from other IDs. Remember, this particular network entity ID should be unique within your infrastructure. It should not be shared by another device. Now, the second thing we need, because let alone we're going to configure traffic engineering, we'll need to we need to configure a metric style. In Huawei, it's called cost style, but in Cisco, it's called metric style. We only have to narrow and wide. So we have to use wide because it gives us extension to be able to use MPLS traffic engineering. But if you want to just do basic MPLS, you can decide to go with narrow. So the cost style here that we will use, is, if you can see, we have a lot of options, but we are going to use wide, and then we will have to do. I've decided to go with level 2 because we know we have level 1, 2, and level 2. So we're going to use level 2 for simplicity. So the IS level for us will be level 2, and then I want to give this particular device an IS name, just to instead of us having to see this long ID when you're displaying ISIS peer, we have to display the name of the device itself. So we can give it an IS name that is corresponding to our system name, and then that's it. We commit. We commit. So after committing, Huawei has this amazing feature where you can just give this command and be able to see what we've configured under ISIS. And as you can see, we have been able to configure our level, our cost style, our network entity, and the IS name. Now the next thing we do is we have to configure ISIS under the physical interfaces that are participating in our MPLS and the loopback interface. So we exit from here and go to interface loopback 0. We have given it an IP address of 1.1.1, it's a /32, and then how we enable MPLS on interfaces in Huawei, you just say ISIS enable and then the process ID, which we gave it as 1. Okay, and then you go back to interface is 100 ISIS enable 1. Then we go to interface 101 ISIS enable 1, and then you commit. Once you do that, you'll be able to have appearing. So if you issue the command, there's one thing. The reason as to why we will not have appearing form just yet is because if you go to Tanzania, let me go to Uganda. If you go to Uganda Uganda P02, for example, you remember ISIS has 2 network types: point-to-point and the broadcast, which is the default. So I've decided to go with point-to-point. That's why it's not coming up. So if we have mismatch in network type, then the peering will not come up. So you have to ensure that the peering is the same. So if you show run E00, show run interface E00, the ISIS network type here is point-to-point. So equally, we'll have to go and configure the same in Rwanda. So let's go back to Rwanda. Let's go to interface Ethernet 100, and then we can give the command ISIS, I think circuit type, and then if you see, you only have one option, which is point-to-point. The same thing we do on Ether1. Give the command ISIS network circuit type point-to-point, and then you commit. Now after committing, you will now go back and give the command again, display ISIS peer, then you have your pairing up. That's done for Rwanda. Let's go to South Africa PE05. Now here we have to also configure ISIS. So you go to config terminal, conf t, and then the command to start the process is router ISIS. You can also give it a process ID. Let me just, for simplicity, just give it 1. And then also here we need a network entity. We can give it 49.0 200 000 and then the last one is it doesn't change. This 0 here doesn't change. Again, this is not an ISIS lab, so please, in case of any questions about ISIS, we can tackle them at the end of this. But let's just wait for the Theophilus to come back and give us a lab on that. So after enabling the net, we'll also have to enable. Remember, in Huawei we said the cost style has to be wide. In Cisco, the command is metric style, not cost style. So we can say metric style. Then options here we have narrow, transition, and wide. We have to choose wide because we'll do MPLS traffic engineering later. And the other thing is we have to do the IS level. In Huawei, it's IS level, but here is IS type, and we only have 3 options here. We have to choose level 2 only because that's what we're using within MPLS core. Then after that, I'm not sure we are missing anything. We just go ahead and confirm that everything is fine. We configured our net, configure our type, and we've configured our metric style. That should work for us. That's all we need for this one. So we go within we go under the interfaces that are participating in MPLS. That is G02, G03, and the loopback interface, and enable ISIS. So conf t interface loopback 0. The command to enable ISIS in IPv4 is IP router ISIS, then the process number. Then you go to interface gig 2. Then you give the same command, go to interface gig 3, that is this interface connecting to TZP04. You give it IP router ISIS1, and that's it. You are done. ISIS is configured, but again, we will not be able to show IP route. We will not be able to get the ISIS. Now this is part of troubleshooting. We will not be able to get ISIS routes because if you go to, we've not enabled the network type. It should be point to point. That's why we're not getting any. We're not getting any routes. So let's go back to the physical interfaces. Interface gig 2 IP no ISIS network point to point. Interface gig 3. Now you can see even that this comes up. Interface gig 3 ISIS network point to point. Then we are done. Then you remember to save your configuration. So if you say show IP route, now we can get routes. You can actually narrow it down to only routes learned via ISIS, and you can see we're getting routes from PE01, routes from P02, P03, and then TZ04, and then the physical interfaces. So we can actually ping ourselves, and we can ping we in South Africa, we can ping our PE in Rwanda. So ping 1.1.1, and we have reachability. Okay, we can even do a trace. There you go. We can be able to reach our PE in Rwanda. So we have done. We've completed this particular part here. So we can mark this as green. So now the next step is to enable MPLS in the core. The next step is to enable MPLS in the core. So any questions before we move on? No questions? Okay, let's proceed. Let's proceed. So now the next thing we're going to do is now to enable MPLS. Krishna, I've seen your question about why SIS is point to point. Now the broadcast one, they have to elect a DIS the same way we have to elect a DR in OSPF. And that if because we're not dealing with them, we are not dealing with them. Let me say, how can I put it? So first of all, point to point will enable the pairing to come up faster, because for the broadcast one we have to do the election of who will become the DIS, and that might take time. And especially if you're dealing with a large network, then you just need pairings to come up quickly. So that's why we're using point to point, just to speed up the process, and then there's no need to configure broadcast, because the IP addresses here are different. So this is a different subnet, a different subnet, a different subnet, another different subnet. So point to point is ideal for us, and that is basically what you will get in a service provider environment. Okay, let's proceed. So now we want to configure MPLS. As you might have seen, I think it takes a lot of time to configure IGPs and interfaces. The MPLS part is actually very simple to configure. So we start in Rwanda. We now want to configure MPLS in Rwanda. Let me clear the space for us here in the screen. So how we configure MPLS in Huawei is different from Sorry, I had to mute because someone is making a lot of noise. So how we configure MPLS in Huawei is a bit different from how we configure it in Cisco. So in Huawei, let me display version here. We're using this version here. So in Huawei, the configuration of MPLS, first of all, you have to give the command you have to assign the node LSR ID, label switch router ID. If you just go and say MPLS, it will give you an it will actually work, but for it to be able to work properly, you have to give it an MPLS LSR ID. So we go back and say MPLS LSR ID, and then we give it an ID, which is in this case the IP address of the loopback. That is the preferred one because of uh, the reachability aspect of it. I said we prefer giving the LSR ID as the loopback interface of that particular node, and it has to be advertised in ISIS, or if you're using SPF for it to work. So our loopback interface should be at a /32 interface again, and we had given it as 1. Then from there, we go and MPLS and say we can enable MPLS LDP, and that's it. So we have to enable them globally, and then from there we go into the interfaces, physical interfaces, and enable MPLS. So we go to interface Ethernet 100 and give the command MPLS, and then the command MPLS LDP. Okay, then you go to interface Ethernet 101, give the command MPLS, the command MPLS LDP, and then you commit, and you're good to go. That is done. We can't enable MPLS. I know someone maybe might ask why not to enable MPLS on loopback. It doesn't allow you to enable MPLS on a loopback. I think if you see, it allows you to configure or to give the command, but it doesn't work. It doesn't work. It takes you back to the global configuration, so it doesn't work. So after that, we go and also enable MPLS in Cisco. This is Cisco. So there are two ways of enabling MPLS. You can either enable MPLS under the IGP process, or you can enable MPLS under the specific interfaces. So we're going to do both in this case. So for Uganda PA02, we're going to enable MPLS under the specific interfaces. But for South Africa PA05, we'll do it under the LDP, so under the IGP, so that you can get flavors for both. So Uganda, the interfaces that are participating in MPLS, we have E00, E01, and then E02. Now Cisco, you can actually give the command interface range, then E00 all the way to 2, and then you can give the command MPLS IP. And then immediately you do that for Cisco, you get this notification that MPLS LDP between Rwanda and TZ, that is 11 and 444, are up. So if you go and say issue the command show MPLS LDP neighbor brief, you're able to see your neighboring here. So this is a verification command. So let's go. So as I said, for Tanzania, for this Cisco iOS XR, everything is enabled. Everything is configured. SIS and MPLS. So we just have to do the verification. Show MPLS LDP neighbor. You can actually give it a brief command, and then you can see we are neighbor with 2 and 1. So let's go to South Africa PE and enable MPLS, but this time round, we're going to enable MPLS under the ISIS process. Which so what that will do is all the interfaces that have been enabled, that ISIS has been enabled on, by virtue of that they have been enabled, ISIS has been enabled on them. If you go to ISIS process and enable and configure MPLS, all of them will be able to be automatically have MPLS enabled on them. That's the benefit you get. So the one that you enable under each interfaces could be tedious unless you do the range command like we did. But the most effective one is the one that you enable MPLS under the IGP process, in this case ISIS. So we go back to ISIS. We had given it a process ID of 1, router ISIS1. Let us show run. Let's see what we had configured. So we had configured the net, we had configured the IS type, and then the metric. So the command to enable MPLS globally under the ISIS process is MPLS LDP autoconfig. The moment you give that command, then you should be able to get some notification. There you go. So we are neighbors with 4. Now Cisco gives you, the logs, but Huawei, for some reasons, this one doesn't. I think maybe it's the lab environment. It doesn't give you the logs. But if you go and issue the command show MPLS LDP neighbor brief, you'll be able to see. Now that's strange, and that will actually tell us why we're not neighbors with this particular device. So this is part of troubleshooting, because it can't be all perfect. So let's go and confirm why we are not forming neighbor for between between Kenya and South Africa, these two devices here. So let's see, show run interface. The first thing is, do we have SIS enabled? So show run interface gig 2 IP router SIS. Yes, that's fine. That's fine. Can we ping that IP address? That's IP address in Kenya is .3. Yes, we can ping. So let's go to Kenya .3. So clearly here it says we are forming an ISIS neighborship or peering with our South Africa PE05, but MPLS is not coming up. Display MPLS LDP peer. It's not coming up. So we need to troubleshoot, because we cannot proceed if it's not working. So display current interface ether 02. That's the one that is connecting to South Africa P05. So everything here is fine, except that we have not enabled MPLS IP. Yes, we've not enabled MPLS for this one. Last time we checked ISIS1. No, that's a different one. ISIS1. Last time we checked, we can also do global configuration of MPLS under in Huawei. So I think the command here is MPLS autoconfig, but it says you have to enable MPLS. Now this is what I wanted to show you earlier, but I skipped it. If you just go and enable MPLS under the SIS, you have to enable it globally first for Huawei. So let's go and do that. So we have to enable MPLS. LSR ID is 3, and then enable MPLS, and then enable MPLS LDP, and then you commit. Okay, then you go back to ISIS process ID 1, display this, and then you say the MPLS LDP autoconfig. That should be able to work for us. Now, if you go back to South Africa, earlier on we only had 4.4.4 as a neighbor, but if you issue that command again, now we have a neighborship with 3, and I think even in Uganda we have our neighborship with 3 also. So that's fine. Now MPLS, basic MPLS configuration has been done and completed within our MPLS core. So now we have to do the verification and see that everything is fine. So the first verification, which is what we've been doing, if you issue the command show MPLS LDP neighbor brief, it gives you all the neighbors that all the nodes that you are neighbors with in terms of MPLS. So we did that in Uganda. We can go and issue that in Rwanda. Display MPLS LDP peer. This is the command in Huawei. As you can see, we are neighbors with 2 and 4. That's okay. That's what we would want to see. If you go to Tanzania, we had given the command earlier, and at that time we only had 2 pairings, MPLS LDP pairings. But now, if you issue the command again, we have 4. So that's okay, because we are pairing with the 01, 02, 05, and 03. Lastly, if you go and issue in Kenya, display MPLS LDP peer, we are done there. So we have 3 pairings. That's fine. And then we had confirmed in South Africa, but I can just go and do it again. So MPLS is done. We are done configuring MPLS. One verification we need now to know is, are we getting labels? Are we able to assign labels to fake? Remember, I told you what fake is during our last conversation. So the command to show verify whether we are assigning labels to different prefixes or fakes is in Cisco. It's show MPLS forwarding table, and you can see we're having our labels assigned. Our labels are being assigned, and then if you go to Huawei, in Kenya, the command is display MPLS LSP. Okay, or if you want to see detailed one, so you can see we are getting some labels here, which is good. If you want to see a detailed one, you can issue the command display MPLS LDP LSP, and then you'll be able to get all these labels here. So earlier on, if you remember, we were able to ping from South Africa to Rwanda, and our output had normal IP. It didn't have any labels assigned to it. But now, let's see if we try and trace the loopback interface of Rwanda P01. Let's see what happens. You can see now we are using MPLS, because it's evident here that the label has been assigned to this particular prefix, which is here. So we are using this path to reach Rwanda. Now, if you recall our conversation about label switched path, LSP, so there are those ones that are established using IGP, meaning LSP will be established based on the IGP's shortest path first. But as we'll be configuring traffic engineering, we'll be able to leverage the use of RSVP, and therefore from there RSVP uses an algorithm called constrain shortest path first. But the normal MPLS without RSVP or traffic engineering uses the path that has been determined by the IGP. That's why IGP is also very important. So as it is now, we have done configuring MPLS, basic MPLS, because we've not done MPLS traffic engineering. We've done configuring MPLS within our MPLS backbone. Now the next task that we had was this is done. The next task now was to be able to do MPBGP, but I think this should come after we do this, just for understanding. And I will be telling you why. Okay, let me just go back here and say this here should come first. So let's do first of all this. Let's configure VRFs. But basically, that's how we configure MPLS. Any questions about that before we configure VRFs or VPN instances in Huawei and Cisco?
Hi, David. I hope you can hear me well.
Yes, Martin.
Say, for example, in the MPLS core, and let's say your IGP is up. In this case will be ISIS. If let's say in Uganda, the interface E0/1 is the best path, and the label switch path goes down. How will MPLS ensure that it chooses another label switched path and bypasses the IGP routing?
Bypasses what?
The IGP routing.
Okay. Okay. So again, if you remember our conversation last weekend about LSPs, we said these ones are predetermined paths. So assuming we've not configured MPLS traffic engineering here, we're just dealing with basic MPLS configuration like we have done. And as we can see, for us to get from South Africa to Rwanda, we are using this this path here. This is what we are using. We're using this path here. We go to TZ, we go to Rwanda. We're not using any other. But the beauty with MPLS is even without configuring RSVP, there is another predetermined path that can be used in case this particular link were to go down, or this particular link were to go down. So in that case, this particular PE device will be able to select again based on, because the ISIS is configured. So there will be ISIS convergency within the MPLS core, and maybe this path will be selected as the next best path, or this path will be selected as the next best path. So that is how it's done, Martin. I'm not sure if I've been able to answer your question well. Or
Yes, yes, you have things. And if we don't have traffic engineering enabled, what will be the default way to make sure that the label switched path is up?
so then, if you don't have traffic engineering enabled, then MPLS will leverage or will depend on the IGP, in this case ISIS, to be able to select the best path based on the shortest path fast algorithm that ISIS or SPF runs.
Okay.
Yeah, we can actually demonstrate that matching for you, because it's a lab, so we can not just for you, for everyone to see. So for us to reach 1.1.1, we're going through this device here, but let's shut down this interface. Let's go to Tanzania P04 and shut down interface gigabit 0001. And now, in fact, we can actually do a continuous ping. Repeat a couple of times and do that.
David,
Yes.
I think
Yes.
for the sake of time, continue with the lab, but I am happy with your answer.
Okay, so we've been able to shut down that interface, and as you can see that we are still able to reach that node. If we cancel this ping and we go and do a trace route, that is not supposed to be the case, because I need to I didn't do anything. I need to shut. Sorry. I apologize for that. I need to go and this is I need to shut this and then commit. This is Cisco XR. We only had one drop and then it came back up, so we can go back and do the trace now. And as you can see, we're actually load balancing. We're going to 3, and then we go first of all to 3, and then we go to 2, then we go to 1, or we can go to 4, and then you go to 2, then you go to 1. Basically, that's how it works. So let's go back and no shut this, and then commit, and end. If you do that trace again, it uses the shortest path. So that's to answer your question, and of course for the benefit of everyone else in attendance. So okay, let's move on, because I can see we only have like an hour before we configure. We're done with this. We said 2 hours, so we have an hour before we're done with this. So now after configuring MPLS, so everything here is fine and we're good. Now we want to configure and ensure that these customers and ensure that these users in Rwanda are able to reach their counterparts in South Africa. And for the PE to CE pairing, this pairing here and this pairing here, for simplicity, we're going to use BGP. But in case we have time, we'll be able to configure ISIS, OSPF. Let me configure, we'll be able to configure OSPF for the CE to PE pairing. But if we don't have time, unfortunately, we can just run through it and the theory part of it. But for simplicity, we're going to configure BGP because already this customer has an IS number. As you can see, there are IS 100. We are IS 2000. As you can see, we are IS 2000. So since the customer has an IS number, so we can go ahead and do a BGP pairing between the CEs and the PEs. And this BGP here will be the normal BGP. And by the word normal, I'm saying, I'm meaning, we'll configure IPv4 address family between these devices and this device here. But between this device and this device, we'll configure BGP, but use the VPN v4 address family, because this is what, by the word VPN, it's virtual private network. This is what will enable us to be able to transport routes from this device all the way to this device. Okay, so let's go ahead and first of all, for us to do that, what we will need, if you go back to our outline here, we need to create VRFs on both PEs. For Cisco, it's called VRFs. For Huawei, they refer to it as VPN instance, as we will be seeing in a few. And then after creating VRFs, we'll do route distinguishers and route targets. Basically, route distinguisher is what is able to distinguish routes. If you had 1,000 customers using MPLS core, you'll give 1,000 different route distinguishers to be able to distinguish those 1,000 customers and distinguish their routes from each other. Then now the route targets is what controls what you import or export. For example, now if you go to our topology, I'm having a challenge when I do this. If you go to our topology, the route targets will be able to determine what we export from this customer all the way to here, and what this customer imports, and vice versa, what he exports and imports. That is the work of the route target, if you remember from our discussion. So quickly, let's dive into the configuration of VRFs or on both PEs. Again, VRF is only done on PEs, not provider devices. We only do it on provider edge devices. So let's start with Rwanda. Since this customer is AS100, we're just going to give it a meaningful VRF name that will be able to help us quickly identify or be able to know that this particular VRF belongs to this customer. So in Rwanda PE, you do it globally. You go and you issue the command IP VPN instance. Then if you use the question mark, it gives you the option to do a string. Now, since this is S100, we can give it a name like S100, okay? And then we're done. Since we are doing IPv4 configuration, not IPv6, we give it an IPv4 family address, unicast. Then from there, the next thing we do, since we're already here, we configure a route distinguisher. So configure a route distinguisher, and this is the format. Now I prefer using the loopback interface of the PE and the AS number of the customer as the route distinguisher. It's easy for you to identify which one it is. So we do it in this format. So this is the loopback of interface of the PE, and the AS number here is 100. The next thing we need is a route target, or in Huawei it's called VPN target. So the command here is VPN target, and then you need to export or import. If you have a different VPN, if you have a different identifier for exporting and importing, then you'll be able to just give that. But if your import and export route target or VPN target is the same, then to save time, what you do, again, how I like doing it is I use the AS number of our service provider and then combined with the AS number of our customer. So our AS number here is 2000, and our service provider, so our customer here is AS 100. Now, since I want to use this particular value for both export and import, I give the command here both, and as you can see, it tells you that we've been able to export value. The export value has been assigned, and then the import value identifier has also been assigned. Then you commit. If you exit out of here and issue the command display current VPN instance, you're able to see the instance that you've assigned. The next thing was, after creating a VPN instance or a VRF, you have to assign this VRF to an interface that connects to the customer. For our case here, the interface is Ethernet 102. So we have to configure, we have to add this interface E012 to.
Sorry, I think David, you're muted, or is it just my network?
No, I'm not muted. Can anybody else hear me?
We are able to hear you, David, clearly.
Just my network.
Okay, thank you. Is it okay now?
Yes, it's okay.
Okay, so thank you. So after creating the VRF, we assign this VRF to the interface that is connecting to our customer, and for our case here, that interface is Ethernet 102. So we go under interface Ethernet 102. The command to assign VPN or VRF to an interface in Huawei is IP binding, and then if you use the question mark, there's a keyword VPN instance, and then you're able to see all the VRFs that you've configured. In our case, we only have one, so we'll have to use that. So once you configure that, you get this information here and a notification that in case you had IP addresses or anything configured under this interface, it will be removed. So in our case, we didn't have anything configured, so we are good. Now the next thing we do is assign an IP address. The order of event here is very important. You first of all assign this interface to a VRF or a VPN instance, and then go ahead and assign an IP address. If you assign an IP address before assigning it to a VPN instance, it will remove that IP address, and then you have to reconfigure it afresh. So first of all, assign an interface to a VRF, and then now assign an IP address. So our IP address we're using here is, if you can see from your screen, is 192.168.19. We're using a private IP address because we're not configuring anything that goes outside the internet. We're just configuring reachability between it's the same interface, not sub interface, the same interface. So we use I was answering a question I saw pop up. So we use a private IP address because they're not going to the internet. They're just enabling connectivity between sites that are geographically distant or separated. So the IP address here, that's why we're using a private IP. The IP address here is 192.168.19, and then since we are in PE01, our last octet or our host IP will be 1, and then it's a /24. We can even give it a description and say this one here connects to CE09 in AS 100. descriptions are very important because during troubleshooting, it enables you to know what you're doing quickly instead of just having to do it all over again. So if you display current interface Ethernet 101, now you can be able to, no, it's 102, sorry, it's 102. You're able to see that this interface now is under VRF. And since we've done that, now our PE device will be able to keep two routing tables, one global routing table and one routing table for VRF AS100. Let's go and quickly confirm that. Display IP routing table. This one shows you the routing table, the global routing table. As you can see, there's no 1 and 2 here. There's no 1 and 2. But if you issue the command display IP routing table for VPN instance S100, you're able to see those particular IP, those particular prefixes under this particular VRF, and it clearly tells you this routing table belongs to S100. The other one, it will tell you it's a public routing table, meaning global routing table. So PE devices keep two types of tables: global routing table and VRF routing table. Now we are done configuring VRF in Rwanda. Let's go and configure VRF in our counterpart in South Africa, PE05 here. So our PE05 show run VRF. As you can see, we have no VRF configured. Okay, so we do it afresh. Okay, so we go to our global configuration and issue the command VRF definition. This is the newer version of configuring VRF. So VRF definition, again, the word here is S100 as the VRF name, and then you enter. We're also dealing with the IPv4 address family, so we can say our address family is IPv4. The same with the same as it was for Rwanda. We also need a route distinguisher and route target for this particular PE. So in Rwanda, the keyword was route distinguisher because it's a Huawei device. In Cisco, the keyword is just RD, and then you go ahead and give your RD in this format, either AS number and any other number you choose, or the IP address and any other number you choose. So for us, or for me, I like giving it, as I said, the loopback interface of our PE device and the AS number of our customer. That's the RD. Now, Huawei's keyword for route target is VPN target, but in Cisco, you actually use the word route target, and you can see you either choose to export or import. But since we're using the same value for exporting and importing, we give the keyword both, and we go ahead and use. I would prefer that we use the same route target values. Those ones don't have to be unique within your service provider environment. You can use them as long as they refer to the same VRF, or just for simplicity, that for VRF is 100 route targets, and for exporting and importing at these values. If you have that in place, then when it comes to troubleshooting, it becomes a lot easier. So in Rwanda, if you display current VPN, we're able to use these values as our route targets. So let's go ahead and just use the same here there for simplicity, just to make things simple. So that's our route target, both. So exit from here and then show run. If you give the command show run VRF, you're able to see your VRF has been defined correctly. We have our route distinguisher, our route targets to export and import, and of course the address family. The second step is to add this interface that connects to your customer, gigabit 1 in our case, to this VRF AS100. So you go inside the VRF, the interface, and say interface gig 1, and then we can say, remember we said, okay, let me assign an IP address here and see what happens. So IP address 192.168.58, and then since we're in PA05, the host IP will be 5.5. it's a /24, and then we no shut this interface, of course. It was not shut. Okay, and then from there we can give it we can now assign it to a VRF. The command is to assign a VRF to an interface is VRF forwarding, and then you give that particular VRF's number. Now look at this message. It says interface on gigabit 1 has been disabled because you've enabled VRF in that particular interface. In other words, you've removed this interface from a global routing table to a VRF routing table. That's why if you do show run interface gig1, you've lost the IP address. There's no IP address configured here, so you have to go back and reissue this command again. And you see the time you're wasting to do that. So that's why the order of events is very important. First of all, assign an interface to a VRF, then assign an IP address. So once you do that, if you go and confirm again the configuration of this interface, now our IP address is correctly configured. So we are done. So it means if you give the command show IP route, this particular subnet, we won't get it. We will not get it because we are looking in the global routing table. But if you say show IP route for VRF S100, that particular subnet is here, and you are. Why did I get 56 from? It's supposed to be 58. Guys, I'm sorry. Let's go back to conft interface gig1. It's supposed to be 58. Do show run interface gig1. No, it's supposed to be 58. My apologies. The IP address here is supposed to be 58, not 56. The third octet, because it's correspond to 5 and 8, so the third octet should be 58, not 56. My apologies. All right, so show run or show IP route. Let's see our global routing table. We don't have 192.168 subnet here because this is the global routing table, but we find it under our VRF table. Show IP route for VRF S100. There you go. Now we are good. It means for us to we can be able. I remember I said IP has been configured, has been pre-configured. So this IP address has been configured on this Huawei device, which means if we've done everything correctly, we are able to ping this particular, and this is how you ping under the VRF. We're able to ping .8 on the other side. Did I do the correct thing? No, it's ping. Yeah, it's ping VRF S100, and then you give the IP address. So if you've done everything correctly, I think it should be able to work. It's not working. No, sorry. We are pinging .9 instead of .8. Again, my apologies. There you go. So it's successful. The ping is successful, which means the PEs can communicate with the CE. So we are done configuring that. So let's go back again and mark. We are done configuring this. So now we go and now configure MPBTP between PE routers, and specifically the PNV4 address family. Let's go to Rwanda. Confirm we can ping the loopback interface of PE05 in South Africa, because that's what we're going to use for BGP peering. Yes, we can ping it. That's good. So our AS number here as Life Technologies is AS2000. So that's what we're going to use under the BGP as the AS number. So the command to configure BGP in Huawei is BGP, then you give the AS number 2000. Okay. Now by default, the IPv4 address family is enabled in Huawei, even in Cisco. So we have to disable that, because we're not going to do the normal IPv4 BGP pairing. We're going to use the VPN-v4 address family. And I keep stressing that because that's what will enable us to be able to transport routes from PE01 to PE05. So after that, we now have to do the peer. So our peer is 5.5.5, and this peer is in our AS number 2000. Therefore, it's an internal peer. I tapped the wrong number. Word there, it's number, not with the double R. And then since we're using the loopback interfaces to do the peering, we issue this command so that we can instruct our process or peering which interface they should be using, because by default it will use the physical interface. But since we're using the loopback interface, then we have to use this command here to instruct our peering to use the loopback interface as the source of this peering. Now, basically, you'll have to configure BGP password for this one, but in the interest of time, I can actually skip that part and not enable or configure password for you, so that we go ahead and just finish in time. Then you commit. After committing, if you do the display this, you'll see automatically it has enabled the IPv4 unicast family. This is not what we want. We want the VPN-v4. So what you can do, you can go under this particular process here, okay, and say peer 5.5.5. I think the keyword is no, sorry, and do peer. Yes, so and then you commit. So if you come again and confirm your configuration, you have disabled this peering. So if you issue the command display BGP peer, you get nothing, okay? Because what we want to configure is VPN-v4. So if you use the help here, these are all the address families that we have that this particular router is able to permit or allow or support. So what we are looking for is an IPv4 family. So let's go back to BGP class and paste and say IPv4 family. But this family here is for VPN-v4 unicast. Okay, and now that you already have the peering, if you say display, now that you already have the peering to configure the peer under the global BGP process, we just are going to say peer 5.5.5 enable. You say yes, and then you can even give the command peer next hop local, and then you commit. Then exit from this view. Under the BGP view, you can issue the command display this. It will show you the configuration you've made. Now this one here is assigned automatically by Huawei because it's able to recognize that we're dealing with VPN targets. So this particular policy here is configure. We need to configure this, if you remember. It's automatically given by Huawei. So this peering here is done on this other side in Rwanda. We go and do the same in South Africa, PE. South Africa PE is here, PE05. Slightly different, but the same idea. So we go to conft router BGP 2000. Okay. Now in Cisco, we are able to disable the default behavior of BGP where it automatically IPv4 is enabled. So we have to go and disable that. So the command to do that is no BGP default IPv4 unicast. You've disabled the default behavior. Then you can go ahead and issue the command neighbor. For Huawei is peer, but the command here is neighbor 1.1.1. You are in remote as myself, which is 2000, and then I want you to use the loopback as the source of the peering, so loopback 0. You configure that. If you go ahead and do the confirmation, this is what we've done so far. Remember, for ISXZ, you don't have to commit. The moment you enter command, it takes effect. For the Cisco NE platform, you have to commit for it to take effect. So this is what we've configured so far. Now, in Huawei, the IPv4 family is VPN-v4. Even in Cisco, it is VPN-v4, but how you enter that view is different. You enter the view with the command address family, VPN-v4, unicast. That's it. Now from here, you come and say neighbor. You can copy this, say neighbor. You activate this neighbor under this address family, activate, and then you can say next hop self. If we did everything correctly, and we did, you get this particular notification that the neighbor is actually up. Now you can go ahead and do verification and say show BGP VPN before unicast all. No routes 8, so summary. And as you can see, that neighborship is up. So that's how, basically, that's how you do this step number 3 here. So we've been able to configure MPBGP between PE routers and under the address family of VPN-v4, and that is done. Okay, and also this one here, we were able to do it. We attached customer interfaces to VRFs, so we're able to do it. As you can see, we are almost done. Now the next part is we have to do PE to C routing or peering. You could use the word routing, or you could use the word peering. And in this case, we're going to use BGP. Okay, so our 6th step is establish PE to CE routing or peering. And in this case, I've decided to use BGP, but as I promised you, if we get time, we'll do configuration for OSPF. Okay, so we are going to do PE to CE peering, and we're using BGP. So let's start with our customers first of all. Let's go to CE09. CE09, we have configured IP addresses, everything is fine. But if we've not configured BGP, if you issue the command show run BGP, show run section BGP, we don't have BGP configured. We don't have BGP configured. If you go to CE08, it's a Huawei device, and say display current BGP, it will actually give you an error or not. So we've not configured any BGP on this other side also. So let's go and do BGP. Let's start configuring BGP in our customer edge devices, because that's the easiest part. So we go to global configuration view in Cisco, and then issue the command router BGP 2000. No, the AS number we're using is 1000. So router BGP 1000. Since we are only configuring IPv4 address family, we just go ahead and leave it the way it is. There's no need of disabling it, because we're configuring IPv4 family. So issue the command neighbor. We're using physical interfaces to do the peering, not the loopback. So because it's eBGP, the preferred one is the physical interfaces, which is point to point. So our neighbor's IP address here is 192.168.19.1, and this neighbor of ours is in remote AS 2000. We are done. But since we have this particular subnet that we want our customers in South Africa to also be able to access, we can go ahead and advertise this prefix here, .90, and of course this prefix between the PE and the CE. And as you can see, CE9 also has a loopback interface. You don't have to advertise it, but if it's a customer route, then you can advertise it. So for the purposes of this particular lab, let's go ahead and advertise the loopback interface of CE09, the LAN interface of CE09. This is 192.168.9.0, and the point-to-point interface IP address or subnet of our peering with our rounder PE. So the command here is network. The loopback interface of this device here is 10.99.9.9 is a /24. So we go and issue the command 10.9.9/24, so it's a 0, and then you give the mask 255.255.255.0, and then we can also go ahead and give this particular I'll advertise our LAN, which is .9, and then we can go ahead and also advertise our direct peering, which is .19 for us, our case. So if you confirm what we have done, push run section BGP, this is what we've done. Okay, so everything should be okay here, and then we save our configurations. Okay, so let's go to CE08. CE08 is Huawei, so it's a bit different, but the same idea. So BGP 1100, they are sharing the same AS because they belong to the same organization. Okay, so BGP 100. I think the best practice will be to configure router ID also manually. So we need to configure router ID here and say our router ID will take this format just to identify. And then we go and say peer. Our peer here is 5. So this is the IP address 192.168.58.5. And then this peer is in our AS number 2000. Right? And then since we also have our networks to advertise, we go ahead and then advertise those. So we say network. Let's start with the loopback interface of CE08, which is a /24. And then we also go ahead and advertise our LAN 192.168.8. Again, we go and advertise our direct peering, which is here 58, our peering between our PE and us. And then you commit. Since this is where you commit, if you display this, this is what we've been able to do. So if you go and issue the command display BGP routing table, you can see these are the networks that we are advertising ourselves. And how we know that is because the next hop is 0, meaning local. These particular networks have been advertised by us. We're not getting them from anywhere, which means as it stands right now, we cannot be able to communicate with our counterparts in Rwanda, that is CE09. We can't, because we've only configured BGP on the CE side. Now we have to configure BGP on the PE side. Remember, this is a PE to CE peering. But I'll just confirm that BGP is configured correctly on CE08. And if you go to CE09 and issue the command show IP BGP summary, BGP, okay, if you BGP, not summary, BGP, it gives you the networks that we are advertising. Again, we know that because the next hop IP address, the next hop IP address here is all zeros. It means we are the ones who are advertising these particular prefixes. Now, let's go to Rwanda. Now we do the PE to CE peering. We've configured on the CE side. We want to configure on the PE side. Remember, this is supposed to, not supposed to. This is these are private or specific routes of peering to specific customers, not the global ones. Therefore, even under the BGP process, we have to also configure it under that particular the address family, which is in this case VPN v4, but the address family has to be pointed to a VRF that has been configured within your PE devices. So in Rwanda PE01, which is a Huawei device, what we already have is this configuration here. We've configured VPN v4 peering within between our PEs, that is up and running. Now we want to configure BGP eBGP peering for a VRF, or within eBGP peering with, not within, with our VRF customer, in this case VRF AS100. So how we do that in Huawei is under BGP process, we give the command IPv4 family question mark. There is this particular keyword, VPN instance. If you give VPN instance keyword, it will be able to give you a list of your VRFs. But in this case, we only have one, so we're going to use our AS100 as a VRF. So once you are under now the VPN instance, BGP IPv4 family VPN instance for VRF, AS100 is the name we give. You can issue the command peer 192.168.19.9. That's the IP address for our CE device. And then this peer is in AS number 100. Now, if you leave it at this, remember, if you remember your eBGP, if you remember eBGP training or topics, eBGP, if you're using the same AS number here and the AS number here, it means when you're exchanging routes, if this device CE08, for example, is sending routes to us, and then when it comes to CE09, we're able to see that our own AS number is listed as part of the AS path, as part of the ASs that it has been able to traverse. We will drop that particular update or those prefixes. We won't accept them because it will appear like they are coming from our own AS number. Therefore, we'll drop it just to prevent or avoid loops within our network. So what we do to override that particular behavior, you can do it either under the service, you can do it under the PE, or you can do it in CEs. But for us, I'll choose to do it under the PE device, and be able to override that particular behavior. And how we do it, we do that is we go and issue this command in Huawei. Huawei, the command is substitute AS. It means if you get AS my own, if I get the AS100, I will be able to substitute it with my own AS, which is 2000. Therefore, we're in Rwanda. If these particular routes are being advertised to CE08, they will go and appear as if they're coming from me. Therefore, they won't be dropped. They'll be accepted or allowed into my device. So this particular command here is very important. So after issuing that command, you just commit. No, we have to advertise the network here also. So the network here is 192.168.19/24, so 0. And then now we commit. If everything is done correctly, I think it's not exit. If everything is done correctly, we should be able to have our peering come up. Yes, and I think it should be coming up. Good. We now have a peering between our PE and our CE device, and we can go ahead and configure from the other side again. That is South Africa PE. So we had configured the BGP VPN v4 peering. Now we want to go and configure BGP, but under our customer VRF, which is AS1000. So let's go back to global configuration and say router BGP 2000. BGP 2000. Let me show you what we were able to do earlier. To show run section BGP. This is what we had configured earlier. We only configured VPN v4 peering between our PE in Rwanda. Now we want to configure BGP peering between our VRF or with our VRF. I keep saying between. We want to configure BGP peering with our VRF. In South Africa here, this is CE08. So this peering has to be done under the VRF. So we're already in BGP configuration mode. So the address family is IPv4, yes, but keyword here is VRF. So we want it to be under the VRF, and our VRF name, if you remember, was S100. Then from there, we can issue the command neighbor. Our neighbor is 192.168.58.8. They are in remote AS. They're in remote AS 100. The same thing we did for Rwanda, we have to do it in South Africa. We have to override that behavior. But we can, as you can see clearly here, there's a prompt that we've gotten a notification that says our peering with S100 is up. But I want us to override that behavior where routes, or I can just leave it so that I can demonstrate what I mean. Let me just leave it there. And come and see what we have in C08. So display BGP peer. That's how you verify. So our peering is established and we're receiving one prefix. We can go and say what that prefix is. As you can see, we are receiving this prefix here. Now you see the command we gave, substitute AS. We were able to substitute that AS with 2000. So this particular one is coming to no, sorry, I'm giving you the wrong information. I'll be able to show it to you once we complete the configuration in South Africa. I've left it like this on default because if you go to CE09 also and say show IP BGP, as you can see in CE09 we're able to get prefixes from CE8. We're getting 8. We're also getting this one here. But if you go to CE08, we're only getting this particular prefix, which is advertised by our PE device. We're not getting customer prefixes simply because of that BGP default behavior, where if it sees an advertisement going to it and its own AS number is attached in that update, it will drop that particular prefix or those particular prefixes. That's why even in South Africa, it's important to give this particular command and say, for this neighbor, I want to do AS override. So once you give that particular command, if you go to CE08, initially we're only getting 192.168.19.0 prefix. We're not getting .9, and we're also not getting 10.9.9.0 prefix. But now, if you issue the command again, it should not fail me. It should not fail me. We should be, yeah, good. BGP is a bit slow, as you may be aware, so it takes time for those updates to take effect. Now, here we only had 19 coming from 2000, but we are now getting 192. Sorry, we're getting .9.0 and also getting .10.9.9.0 from our device. Now, the effect of substitute AS in Huawei and AS override in Cisco is that you can see it appears that those routes are coming from AS 2000. That is what it does, and by that particular configuration, you're able to override the behavior of where those routes are dropped because the AS number, the receiving customer's AS number is seen in an update. So after we've done this configuration and we confirm that we are able to get routes in CE08 and in CE09, let's go there and also confirm we can get routes. So the next important part is to actually do the verification itself. So this customer here is a virtual PC, and the interface, the IP address is 192.168.9.1. Now let's see if this customer, if this user here can be able to ping the server. And the IP address of our server, this is the IP address of our server. Let's see if we can, so this server is in South Africa, and this PC is in Rwanda. Our objective was to enable connectivity or communication between these devices in different locations. So let's go and test that. Now let's go to VPC9, this one here. If you can see my mouse that is hovering, VPC9. Let's go to VPC9 and ping our server. Okay, there you go. So we have reachability, meaning when we are in Rwanda, we can be able to ping or reach this device. Okay, so that's a ping. So let's see which path within our MPLS service provider network. Let's see which route this particular traffic is using. Because as I mentioned, we've not enabled MPLS traffic engineering. Therefore, it will use the default path that has been selected or decided by the IGP, in this case ISIS. So it will use the shortest path. So let's go to, so we did a ping, let's do a trace. Trace, as you can see, we first go to, of course, CE09, that is the IP address there. Then we go to our PE device, Rwanda PE01. Then we go to our Tanzania PE device, this is Cisco ISXR. Then we go to, of course, we exit via, then, so for these virtual images, there are some next hops that they omit when you're doing the trace. For example, here I was expecting, or we're expecting to see 20.1.45, which means PE05, and before it can exit. But we can clearly tell that our traffic is coming this way before it exits. That is what IGP has been able to give us. That is the label switched path that has been predetermined or pre-established by IGP. Let's go and do a ping from this other side also, just to be fair. That is the server. Now, can the server ping our PC? The IP address is 192.168.9.1. Yes, we can. No, 9, not 8, 9. Yes, we can ping. Can we trace? We trace, of course, we can trace, but let's see the path that is being used. Remember we said LSPs, label switched path, are unidirectional. It means if traffic uses this path to go here, it does not mean that the reverse traffic will necessarily use the same path. It can actually use this other path as long as it's the best, or it can just decide to use the same path because, as we said, we've not configured traffic engineering. Therefore, we're using ISIS to be able to tell us which path we're using. Okay, so let's see which path we are taking from South Africa to Rwanda. So let's trace. If you trace, look at that. It goes to our CE8, of course, that is that particular IP address. Then it goes to our PE device. Then for this case, it uses the same path, the same return path to Rwanda. So basically, we've been able to configure basic MPLS without traffic engineering, and we've been able to achieve connectivity between this particular customers' branches. So this particular user here is in Rwanda, this particular user here is in South Africa, and we can be able to communicate with each other. So that is MPLS L3 VPN configuration. It is straightforward and as simple as that. Okay, so let's go and quickly configure L2 VPN. So L2 VPN, what we'll do in this configuration is that Remember we said our customer here is 670, and they have come to us and they have told us, you know what, there's a content in South Africa. We need to get those content from you guys, because maybe it's cheaper for us to get that content from South Africa as opposed to anywhere else. And we don't have an infrastructure that will get us from Rwanda, all the way from Rwanda, because this is Rwanda P01. We don't have an infrastructure that will get us all the way from Rwanda to South Africa. So you guys, that is LifeFit Technologies, you have an infrastructure. Therefore, we want to pay you so that we can use your infrastructure and be able to get that particular content from South Africa. So here's how we do it. It's a very simple one. So kindly, please pay attention. So what we do is we already have connectivity between our PE in Rwanda and our PE in South Africa. That part is already done, because as is so clearly, we could be able to ping .5.5.5 in Rwanda and vice versa. So that part is done. So what we now want to do, we'll have to establish a virtual circuit between this particular interface here and this particular interface. We'll have to establish a virtual circuit, VC in short. Okay, and then between this particular, let me use a different color. Between these particular devices here, we'll have to establish what we call attachment circuit. And also here, we'll have to establish what we call attachment circuit. Okay. Now, how do we do that? Simple. How we do that is, okay, so because we're using, so here we'll have to use sub interfaces. We have to use sub interfaces. So for this physical interface, we'll configure sub interface and give it .670 to reflect our AS number. And also here, we'll configure sub interface .70. The same thing here, we'll configure sub interface, and also here a sub interface. So after doing after configuring the sub interfaces, what we'll do, we'll establish a cross connect between this interface and this interface. Once we establish a cross connect between this interface and this interface, our virtual circuit will be up. So what will happen is, after this virtual circuit is up, this device here, ABC06, and South Africa IGW means International Gateway or Internet Gateway. Basically, this is our internet breakout. So these devices here will be able to will be able to communicate with each other, and how they see this communication is as if this is ABC and this is ZAIGW. That's how they see it. That's how they see each other. They do not really see each other as if they're coming through our MPLS infrastructure. Once this VC is up, this is how they see each other, and therefore we'll be able to configure IP address. Let me clear this one. Let me draw it here. So this is ABC, and then this is ZA. So they will be able to see each other in that way, that this is like a point-to-point connection. Therefore, we can come ahead, we can go ahead and assign an IP address here, and an IP address here, and that IP address has to be in the same subnet, 20.6.7.6/31 subnet here. That's what we are deciding. We are opting to go for. That's what will happen. So let's quickly go and configure after we've understood. Let's quickly go and configure that cross connect. And in Huawei and Cisco, it's done a bit different. So what we'll be able to do, I forgot to mention, we have two types of MPLS LDP peering. We have local peering, which is a peering between two physical connections, like so. And then we have a remote peering, whereby you can peer with another PE that is not directly connected to you. Okay, so those are the two types we have for MPLS peering. So in this case, for us to be able to do the virtual circuit, we have to establish, first of all, MPLS remote peering between PE01 and P05. So let's go ahead and do the configuration, guys, so that we can finish in time, because I can see our time is very much spent. And I'm assuming, because silence means we are going on well, and in case someone has questions, please preserve them for later, because we are about to finish. Now, let's go to Rwanda PE01 and establish that remote LDP peering. This is how we do it. This is we first of all have to enable what we call MPLS L2 VPN. That has to be enabled because we configure MPLS L2 VPN. After enabling that, we jump back out of this and now specifically configure MPLS LDP peering between our PE in South Africa. The command is MPLS LDP question mark. You can see it's called remote peer. So remote peer, and then we specify a name. For our case here, we can just give it a name that it's easy for us to understand. So the name here is P05. Now, we are now under the MPLS LDP remote peer configuration. What are our options? Very many, but the one we're looking for is the remote. Now we have to specify the remote IP. And the remote IP here is the loopback IP address or the LSR ID of P05, which in our case is 5.5.5. Okay, we are done. Now, this particular interface, we said we'll do sub interface. Okay, let's go and configure that. So let's go to interface Ethernet 10.10.03.670. Just like in Cisco, where you have to do encapsulation.1q, here the command is VLAN type .1q, then you give the VLAN ID, and then after you've done that, now this is where you configure the cross connect. This is the command to configure the cross connection. In Huawei, the command is MPLS L2 VC. You give the IP address of the target peer. The target peer is a remote peer. In our case, is 5.5.5. And then you give the identifier of layer 2 virtual circuit. In our case, 670. This particular identifier has to match on both sides for it to work. Commit. Let's go to South Africa. So for South Africa, no, not IGW, but PE05. Conft. In our case here, we can go ahead and first of all give a pseudowire. Pseudowire is how do I explain it? Let's just go and define a pseudowire class. Martin Modiba or Martin Lisha, you can quickly Google, because someone will ask me what a pseudowire class is and why we're doing it. But why I'm doing a pseudowire class is because later on we'll be able to actually influence traffic within our service provider environment, and therefore we'll have to, for this class, we'll have to say that for this particular service, use this traffic to go from South Africa to Rwanda. So the pseudowire class here, we can give it a name and give it a name, for example, L2VPN 670. And then now we define our encapsulation as, we have various options, but we are using MPLS. After doing that, you exit from here. Let's take note of this pseudowire ID. Let me just copy it. Now we go and create our sub interface. This interface is gig 4, so it's gig 4.6. First of all, let's not shut this particular. It's not shut down, so it's okay. So we go and do interface gig 4.670, and then encapsulation.1q, the VLAN ID 670. Now, in Rwanda, we were able to give this command, MPLS L2VC, and then we gave this command as a way of establishing the cross connect. For Cisco, it's done a little bit different. You actually give the keyword xconnect, and then it asks you for the peer IP address. Peer IP address is, in this case, 1.1.1. And then now, this is where the virtual circuit ID has to match. In this side, we used 670. In this other side, in PE05, we also have to use 670. Then you go ahead and attach the pseudowire class that we had defined up here which is L2 VPN 670. So sudo class, and then you give it a name. That's the guy. If we have done everything correctly, we should be able to have connectivity. So where did we get it wrong, guys? The show run gig 4. The show run interface gig 4. Aha. The difference is that we did not enable ISIS in this particular interface. That's why the interface will not come. So let's go back and do that. This is part of troubleshooting. Although that's very strange. It came up. It came up. Do we need to enable? Do we need to enable? No, we don't. We do not. We do not. So let's go and confirm that our virtual circuit is up. So show MPLS L2 transport is the command in Cisco. Virtual circuit ID is 670. Yep, that is up. If you want to see the details, you can give the detail keyword. The detail keyword. Let's see. So let's expand this. So our the destination is 1.1.1, quadruple 1, and then the virtual circuit ID is 670. It is up. You can see labels are being imposed, meaning because we are using MPLS, and the default path is active. Now the default path has been used by has been established or determined by our IGP, and everything here is just to show you how long it has been up for. The signaling protocol is LDP, and yeah, these are just the confirmation and things that you should be able to relook during your own free time. That's how you confirm that particular peering in Cisco. Not peering, the cross connection. So the virtual circuit is up in Cisco. For Huawei, you give the command display MPLS L2 VC, and then you give the VC ID. So this also tells you that the attachment circuit is up, the VC is up, and it also gives you the time that this VC has been up for, and when you guys the last time the virtual circuit has been up. So this is important for troubleshooting. You need to know how to interpret this particular command. So we've established our virtual circuit. So now let's go and configure the CEs. Let's go to ABC. Show IP interface brief. We only have we don't have a sub interface. Let's go and configure that. So conft I'm rushing because of time. I want to keep it up. Conft interface Ethernet 03.670. This is where we actually configure IP addresses here. For L2 VPN, if you remember, we said that configuration is done solely by the customer. Okay, but in our case here, since the customer wants to pair with us, then they will have to configure their site, the IP address. So we give them the IP address to configure, and we also configure our site. Okay, that is but for the legacy VPN, L2 VPN connection, like down here, this is the customer. This is the customer. The IP address they decide to use is actually theirs, not ours. Ours is just to provide connectivity between Rwanda and South Africa. So the configuration is done here for the IP. The IP also done here. Then they can be able to ping each other. That's it. But the option we've decided to go with today is where we are giving IPT services, that is Internet Protocol Transit services for this customer. So basically, they are transiting our infrastructure to be able to get the content that Google and Meta are offering. Okay, So let's go and finish our configuration. So if we go to ABC, so the sub interface is 670. We also give the command encapsulation.1q 670, and then now the IP address that we are using, if you can see from my screen, the IP address we are using is in this range. This is not this range. This is 676, and then also 676. So this end here will be .6. It's a /31, guys. /31. So this end will be 6, and this end here will be 7, corresponding to the device number. This is 7. This is 6. Okay. So let's go and configure that. So the IP address is 20.6.7.6 this side. It's a /31. I think Evie will be very proud because we are also doing subnetting here if she's in the audience. But it gives you a warning, although you just ignore it. It just tells you that you should be able to use it cautiously. So that IP is done. And then we go to now our IGW, Internet or International Gateway, our Internet breakthrough, under this particular physical interface, and create a sub-interface. So currently it's not there. If you display IP interface brief and you exclude down, you also exclude L3 VPN. This is what we have. We don't have that sub interface here, so let's go ahead and create it. Interface, sorry, Ethernet 102 dot. That's the correct one. The wrong one. Yeah, 02.670. Since this is a sub interface, so we have to give it a VLAN. Like the way we're doing it in Cisco, encapsulation.1q. The command here is VLAN type.1q, then the VLAN ID, and then now we can go ahead and configure the IP address. IP address here is 20.6.7.7.31. Again, you get the same warning here, but it will accept the command. Commit, display this. So this is the IP address we've configured on this side. Can we ping ourselves? Just to confirm, ping. Yes, we can. Can we ping now? Our virtual, remember, we confirmed that our virtual circuit is up. Okay. We also confirmed that our attachment circuit is up. Our attachment circuit here is also up. If you forgot that, then we can just go and confirm it in Rwanda. We confirmed it here that our attachment circuit is up, our virtual circuit is up. Therefore, if we did everything correct, it means in our IGW, this is the IP address, we should be able to ping ABC06. Let's confirm that or verify. So ping, we were able to ping ourselves, but the IP configured here is .6. So can we ping .6? Sure enough, we can. So you remember, I told you guys that when it comes to L2 VPN, this particular service provider infrastructure becomes like a big switch. Basically, it's as if we are connecting these devices using a very big switch. Okay. Therefore, even when you do the trace, remember for L3 VPN, we were able to have all these hops. Like we're able to see how traffic flows from our device all the way to the other end. We can see the hops. Like we had like about 6 hops. Now the beauty with L3 VPN is if you're doing the trace. So we did the ping here. So let's do the trace. It will only show you 1 hop. Don't take my word for it. The command is tracer. Then now, it will only give you 1 hop because, like I said, our service provider environment is appearing as if it's a very big switch. Therefore, even for the trace, it will tell you that we only we're going through one hop for us to reach this is South Africa, Rwanda, which, by the way, physically it's not the case, because as you can see, we have so many devices here. So maybe this traffic is coming via this route, goes here, or it's coming via this route and then it comes here. But the customer doesn't know that. Doesn't know that, because for them, it is our infrastructure is transparent. So after we establish connectivity between our HW and our customer ABC06 device, now I can configure BGP. Remember, in South Africa, if you display current configuration BGP, we already have BGP pre-configured, and we are pairing with Google. That is the IP address, and we are pairing with Meta. That's the IP address. So even for BGP routing table, even for BGP routes, so because these are Google and Meta are upstream providers, they're giving us a default route, meaning they're giving us the full routing table. Everything that they have, we get. And let me just show you the configuration for Google. Show run section BGP. This is what we've configured for BGP with our neighbor, and also Google and Meta have a direct pairing, so that if they want to communicate with each other, they do not have to use us as a transit AS. When we have the BGP session, which I hope Martin will take over, we'll be able to see how you can prevent yourself from being a transit AS. That when Google want to go to Meta, they go directly. They don't have to come to us, because being a transit AS can be disadvantageous in so many ways, as you'll be able to see. But now I'm digressing. Let's go back to our discussion. So we already have pairing between our HW and Meta and Google. That's okay. So which means in our HW, we are receiving the entire routing table from Meta. This is Google and Meta. Now we want to establish a BGP pairing between ourselves here in HW07 and our customer. So let's finish the BGP pairing here. The BGP AS number is 2000, and this is what we've already done so far. Now we just have to configure pairing between ourselves and that device in Rwanda. So the command is pair. We're using physical interface here also to pair, because we already have communication between those devices, as we saw a few minutes ago. So the PIP is 67.6, and then the AS number 670. That's it. You commit, and then if you display this, we are able to see that we have that pairing here, and it's actually enabled under our IPv4 family unicast. Now let's go to ABC. We were able to confirm earlier that we don't have any BGP configured. Now it's not configured, so let's go and configure BGP. Configure. Let me see the do show IP route. These are our own routes. Connected and local are just our own route. So router BGP 670. Neighbor. Our neighbor is this ZHW07. The IP is 20.627.7. This neighbor of ours is in remote AS 2000, and we should be having our neighborship come up in a few. There we go. We have our neighborship with that device. We can go ahead now, because as you can see clearly, this particular company here, company ABC, they also have their own subnet that they have been able to be assigned by Afrinic, because they're in Africa. So they have been given up the block 203.0.113.0/24. So they've been given a /24 for them to be able to use within their enterprise environment. Therefore, we go ahead and advertise that particular prefix or block because it belongs to that particular customer. So network 203.0.113.0 mask is 255.255.0. All right, so let's see what we've done. Show run section BGP. So we've done the neighbor, the network command with the neighbor, and we can actually confirm that show BGP. We can confirm that we are getting prefixes. Also, because Google and Meta are giving our transit provider the full routing table, that is 0.0.0/0. We're also able to get it. If you recall the default behavior of eBGP, routes that have been received from this particular devices automatically are advertised to my other eBGP neighborship unless there's a policy to be able to prevent all or a few routes or prefixes from being injected into your BGP routing table. So now let's go and establish what we have in Google. Show IP route. What do we have in the routing table? So we have in the routing table. I want to exclude BGP. No. Anyway, let me just do it. Show IP route will give you all these routes. So we have, or better still, you can say show IP interface brief. So these are what I went ahead and configured loopback interfaces to have many prefixes or many services that our customer ABC can be able to reach. So these are just dummy prefixes, just to give us an idea of how the BGP routing table looks like in Google. And then also in Meta, I went ahead and did the same. Enable, show IP interface brief. As you can see, they are all similar with an exception of this particular loopback here. So this loopback 5 is 200.1.1.11.11.11. It is not there in Google. The reason why I did that is because you will find that maybe there are services that can only be reached via Meta, or maybe there are services that only Meta has, and which is not a rare thing. It's actually possible that we could have a service that Meta has, but so Meta has the service, Google does not have that service. That's why I have gone ahead and configured a loopback interface in Meta and advertised it so that we can be able to reach it from our customer. Now, so as it stands right now, if you go to our ABC customer, these are all, all the, I think I need some water. We've been talking for long. So this is what we're able to receive from our peer. As you can see, the next hop here is 20.6.7.7, which is our peer in South Africa. We are receiving a default route, which is basically full routing table. Now, the common thing that we normally check for IP for internet reachability is we ping Google, which basically we ping 8.8.8. So let's go ahead and do that because 8.8.8 is here in Google and also in Meta, which means Meta has we lost network connection. Sorry guys, we had a flap. We had a flap. Can everybody hear me now? Okay, thanks, Martin.
Yes,
so
yes,
as I was
yes.
saying, so let's go and test connectivity. Let's go and test connectivity. Now that we've done the configurations and everything is fine, and we have confirmed we are receiving the default route, basically the entire routing table, we want to go and ping and see if we can ping 8.8.8. That particular prefix, as I said, is in Google and Meta. So let's go and see if we can ping it. So ping 8.8.8.8. Fingers crossed, this should be working. It is not working. It is not working. Why is that? It is not working. Why is that? Anybody can give me an answer? Why do you think it's not working?
You might not have a root there.
Sorry?
You might not have a root there.
Martin, I can't hear you.
You might not have a root there.
Either you're too close to your microphone.
Oh, is that better?
Yeah, go ahead.
You might not have a root there.
Yeah, that's one possibility. So let's see in Google. Show BGP. Yeah, it's true. I have no way of going back. Let me go to Meta. Show BGP. Yeah, I have no way of going back. And there is and just quickly, just in the interest of time, how to fix that is when this customer, when our device, this service provider device here, the IGW, is pairing with Google and Meta. As you can see, as per the configurations here, okay, these are the configurations here. Now, this particular prefix here belongs to us as Lifey technology. This is our prefix. So we need to be able to advertise this prefix to BGP for us to have connectivity. That is the simplest way to resolve this issue. So let's go ahead and do that. Let's go to IGW 07. We're already there, and then let's advertise our prefix. Network 20.6.7.6 was it? I think, yeah, /31. And then we commit. So initially, let's examine the BGP routing table of Meta, Google. We don't have that prefix here. Okay. And equally, if you go to Meta, we also don't have that prefix here. But now, since we've done that change, let's look again and see. Look at that. We have that prefix installed in Meta, and we also have that prefix installed in Meta. Now let's go and confirm that particular connectivity again. There you go. We are able to reach 8.8.8. Let's trace. Let's trace. If you do a trace route, there you go again. So we are going to, like I said, for L2 VPN, this one here becomes like a switch. So these devices here appear as if they are directly connected point to point. That's why our next hop is .7, which is this IP address here, and then it goes to .6, 142.6, which is this particular IP address. Basically, that's how you leverage the use of MPLS L2 VPN, specifically PWS, Virtual Private Wide Services, to be able to give IPT transit services to your customers. Questions? Questions, so that we only have like 20 minutes for us to configure MPLS traffic engineering. It's a simple task. Any questions? Okay, so I can go ahead and configure MPLS traffic engineering. Everybody's okay now? Because we've done this part up to here. that part up here. So what is what is left for us to configure is MPLS traffic engineering.
Yes, let's proceed, David, and then we can pick the questions at the end.
All right. Okay, thank you. I think my screen is static. My screen is static. My screen is. What are you guys seeing on your screens?
We can see the what will be covered.
Yeah, I think there's something I missed. There's something you guys missed. Let me stop sharing. There's something you guys missed. Ah, no. This can't be happening.
David,
Yes.
I just got one question, man.
Okay.
Yeah, sorry, I was not aware that my microphone was not allowed on the app when you requested for us to ask questions. Yeah, here's my question. Do you see SD-WAN replacing MPLS in the next 5 or 10 years?
I think Martin Modiba was able to answer this question the last time we had that session. Would you kindly just allow me to give him that opportunity for him to answer it?
Okay, thank you.
Okay, Martin, you'll be able to answer that after I'm done presenting, right? If that is okay.
Yeah, sure.
Okay, thank you, guys.
Okay. Now, MPLS traffic engineering. What we've covered this so far. We are now at 8 and 9. So let me 9 just verification. So let's just do this. MPLS traffic engineering. If you remember, we said that MPLS traffic engineering basically gives us the control to be able to influence how traffic moves within our service provider network. Now, if you've been paying attention, and I know you have been paying attention, when we did the traceroute from CE09, this was the path that was used to go to CE08, and also the return traffic was able to use the same path. This is simply because we were depending on IDP to give us the best path, which in their case, the best path is the shortest path, irrespective of whether there's bandwidth issues, whether the link is congested or not. IDP will give you the best path based on cost. Unlike MPLS traffic engineering, whereby as a network engineer, you have control of how your traffic should be able to move within your service provider environment. Now, that is what we are going to do right now. And as you can recall, all the configurations are done within our service provider environment. There's nothing that we touch. From now here on, we are going to use to do configuration within our service provider environment. We are not going to do anything within within our customer enterprise networks. We are only going to concentrate here. Now, we need to enable MPLS for MPLS traffic engineering to work. We need to enable RSVP within our service provider environment, and RSVP is both enabled globally and enabled within the interfaces or under the interfaces that are participating or that you want MPLS traffic engineering to be able to be configured. So we'll do the global configuration, and that will take place inside our LiFi technologies backbone. And let's quickly enable MPLS traffic engineering in Huawei. So let's start with our PE. So the commands we already let's see what we have. Display current include MPLS. So far we have MPLS already, MPLS LDP, and then we've configured, of course, the virtual circuit. But now what we want to configure is MPLS RSVP, and that is enabled under our MPLS view. And the command is, first of all, you enable MPLS TE, that is MPLS traffic engineering. And then second, you enable MPLS MPLS RSVP TE. Okay, that is the global. You first of all enable them globally, and then you commit. Only two commands. You commit. Then after doing that, the reason as to why ISIS and OSPF are chosen as the preferred IGPs in service provider environment is because, like I mentioned, they have extension to enable you configure MPLS traffic engineering. Okay, so we go after enabling that, you go to the interfaces now, the physical interfaces. In this case, is E100 and E101. So interface Ethernet 100, and then MPLS, enable MPLS TE, MPLS RSVP TE. Then go to the other interface, MPLS TE, MPLS RSVP TE, commit.
I don't know if I'm the only one. I can't see your screen moving while you're doing the configuration.
Oh, yeah, you're actually right. You're right. Just give me a second. Give me a second.
Okay.
Just give me a second. Let me change my provider here. Give me a second. I think the issue is the internet. I apologize for that. I was expecting us to have a very good session today. It is okay. Okay. Is that okay now?
Yeah, it is. Thank you.
Okay, thank you so much. Thank you for raising that. So we've done. Okay, since you missed the configuration in Rwanda PE, you'll be able to get that configuration in KE PE because it's Huawei. So I won't go back and do the configuration again. So let's just go ahead. So after that, we go to. So first of all, you enable MPLS globally. Then you go to the physical interfaces and MPLS TE and RSVP, and then you go to the physical interfaces, enable MPLS and TE and MPLS RSVP TE, and then you go inside the ISIS process.
Your screen sharing has disappeared.
What is happening?
You can just reshare again so that we confirm.
Yeah, I think my provider is really messing me up today.
Who is your provider?
Is it now okay?
Who is your provider?
Yeah, it is. It is okay now. We can see.
Martin, my brother.
We can help your provider to fix
potential employer.
We can have a solution
I don't want
for
to be
you.
in trouble with my potential employer. So no, it's not Zuku, Nathan. It's not Zuku. Okay. How is that? Are we good now?
Yeah, good to go.
All right,
we are able to see your screen.
So again, my apologies, guys. That's not what we had planned for this particular session, but well, it happens and we have to deal with it. So let's recap. First, we enable MPLS TE and MPLS RSVP TE globally. Second, we enable it under the physical interfaces. And then third, you go under the ISIS process or SPF if you're using SPF, but we're using ISIS, and enable MPLS TE. And this is how we do it in ISIS. You use the word traffic engineering, the keyword traffic engineering, the command. And since we're using level 2, we use level 2 as the option. That's it, and you're done. So since you missed the whole configuration in Huawei, let's go and configure in this is PE01 Rwanda. Let's go to Kenya P03 and configure because it's Huawei. So Kenya P03 is here. So we enable MPLS TE globally. No, we go to MPLS view first, and then we enable MPLS TE globally, enable MPLS RSVP TE, and then you commit, and then you go to interfaces. We have 3 interfaces, so that's Ethernet 100, MPLS TE. First of all, it says enable MPLS in the interface view. Oh, sorry, MPLS, then MPLS TE, MPLS RSVP. Look like we had not enabled MPLS there. And then we go to 1, MPLS, MPLS TE, MPLS RSVP TE. Last one is 2, MPLS, MPLS TE, MPLS RSVP TE. We commit. That's how you enable MPLS. Now we go to the ISIS view and say ISIS, our process ID is 1, and then the command is traffic engineering level 2 because we're using level 2. Commit. We are done with that configuration in Huawei. So the next one is Uganda. As I mentioned before, our Cisco ISXR configuration is completely done. There's nothing we're doing there. That one was done because of the interest of time. So let's go to Uganda. So Uganda is a Cisco router. It's done differently in Cisco. The first thing we need is we need to enable MPLS traffic engineering globally. And then now we enable MPLS traffic engineering and MPLS traffic engineering and MPLS RSVP inside the physical interfaces. Then third, we enable it inside our IGP process, in this case ISIS process. So steps are the same, but the way you do it is different. So let's do it in Cisco ISXZ. So we enable MPLS traffic engineering globally with this command. That's the command. And then after doing that, all the interfaces that are participating in MPLS, we enable MPLS traffic engineering and RSVP in those interfaces. Now Cisco enables us to do the range command, so we can do interface range. We have E00 all the way to 2. We can do MPLS traffic engineering tunnels, and then we can do MPLS IP. No, it's IP. Can do IP RSVP bandwidth. That's how we enable it. So if you want to someone is unmuted. Someone is unmuted. Thank you. So if you want to, you can go ahead and preserve some bandwidth here, but let's just go with the defaults because of time. Maybe we can get another chance to talk about MPLS traffic engineering itself, but for now, let's just use the default configurations. So we enabled MPLS under the interface. This is how you enable it, this command, and then RSVP under the interface by that command. Lastly, we go and do under the router ISIS process. And here we have to issue 2 commands. The first command is MPLS traffic engineering, basically router ID. We have to give the router ID, which in this case should be LSR ID, which is the loopback interface. And then again, we enable MPLS traffic engineering, because we are using level 2, and then we are done. We are done just like that. And then now lastly we go to South Africa PE. Basically, this is how iOS exists, so the configurations are the same. So I'll be quick here. Conf team, MPLS traffic engineering tunnels. No, it's tunnels. Then interface range, I think it's gig 2 to 3. MPLS traffic engineering tunnels. And then IP RSVP bandwidth. And then we go under ISIS, no, it's router, ISIS1. We give it MPLS traffic engineering router ID, which is our loopback interface, and then under the ISIS level, which is level 2, and then we are done. MPLS TE and MPLS RSVP is enabled on our end. So now we can go ahead and now configure tunnels. We can configure tunnels. And in this case, I want traffic coming from CE02, sorry, CE09. I want that traffic coming from that particular CE to use this path. And then come down here. Then go to CE08. And for traffic coming from CE08, I want it to use this path. It can come here, and then come to this path, and then come to this path before it goes up here. That's what that's our requirement. So what we need to do is in Rwanda we'll create a tunnel, and also in South Africa we'll do a tunnel. So in Rwanda, let's go and create a tunnel for us to be able to use that tunnel to influence how traffic will move, because the blue and red tunnels are the optimal ones based on our customer requirements. So let's go to Rwanda, and the command here is interface tunnel, and we give it a name. Because it's going to P05, we can give it not a name, a tunnel number 005, and then we'll be able to let's configure this tunnel to use the IP address of our loopback, which is 1.1.1. So how we do it is IP unnumbered, no, IP address unnumbered, unnumbered address, unnumbered interface loopback 0. And then what we need to do is we have to tell our router that this particular tunnel is supposed to be used for MPLS TE. So the command will be tunnel mode, tunnel protocol, sorry, MPLS TE. And then this tunnel requires a tunnel ID. In Huawei, you have to give it a tunnel ID. So the command is now MPLS TE, tunnel ID, let's say 5 to correspond with the 5 here. Now, this tunnel has to have a destination. And this tunnel, we want it to go all the way to PE05. So what's the destination? Destination is the loopback interface of PE05. Now, since we are configuring that tunnel from Rwanda to PE to South Africa, the Rwanda PE becomes the head end, the South Africa PE becomes the tail end. Then we can commit. Let's see what we've done so far. Display this. Now, one thing we should have configured is an explicit path. So MPLS TE uses an explicit path. So we're going to use the explicit path from Rwanda PE 01 to South Africa PE 05. The configuration is explicit path. You give it a name. You can say path to maybe path to CE08. Let's give it a name that we can write, path to CE08. Now we have to explicitly issue the IP addresses or the next hops that this traffic will be using. And for our case here, we are in Rwanda, so our next hop, because of the blue one is what we said should be sorry, the red one. Our next hop here is 20.1.12.2. So next hop, the keyword is next hop 20.1.12.2, and then from there it will go all the way to PE03. So the next hop here is 23.3, and then from PE03 it goes down to 35. This particular one here, 35. So that is 35.5. That's it. It has, we already in South Africa. So commit, go back here and go back to our tunnel. What have we done so far? So MPLS TE. Let's tell this particular tunnel to record labels at every hop it goes. It has to record for us the labels, and then now the key command here is MPLS TE path, and then we have to do an explicit path. Then we give it a name. The name here was, you copy exactly what is here, path to C08, and then you commit. If everything is fine, this tunnel interface should be up. Display interface tunnel 008. No, it's 5, not 8. 5. So our tunnel is up. Because why is our tunnel up? Because this particular explicit path is valid. So we go to 2, we go to 3, then we come to 5 before we can exit out. So after creating the tunnel, that tunnel cannot be used until you explicitly use it. But first of all, let's just do a trace and confirm that indeed our tunnel is using that particular path that we've assigned. And look at that. We are actually using our explicit path. We are going to 2. From Rwanda, P01, we go to Uganda, that is 2. We go to Kenya, that is 3. And then we come down to 5, South Africa, that is 5. So our tunnel is working and it's using the route that we have explicitly told it to use. So how do we ensure that this particular tunnel is used by our customer? Simple, 2 things. We first of all configure a tunnel policy, and then in that tunnel policy we explicitly tell that tunnel policy to use this tunnel. After doing that, we go inside the VPN instance of our customer and reference that particular tunnel policy. And that's how, and here's how we do it. We come with a we configure tunnel policy, give it a name. We can give it a name like bind. Let's give it a name that has this particular one. So that bind tunnel 005. Okay. So from here we say tunnel. What are the options? Binding and destination is of course it is going to 5.5.5. That's our destination, and that is for traffic engineering. Now we give the tunnel interface, and then we commit. So let's see what we have done so far. Commit, display this. So we've created a tunnel policy, giving it a name. This is our name. Okay, and then inside that tunnel policy we have said this tunnel should be bound. I think if my teacher of English was good, I think binding and bound, I think I'm getting it correct. So that tunnel interface should be bound. Sorry, the tunnel policy should be bound and use this particular tunnel interface for traffic that goes to 5.5.5.5, which in our case is South Africa PE05. After creating this tunnel policy, now we go inside our customer VPN instance or VRF and reference that particular, or be able to explicitly tell our customer to be able to use this tunnel for the traffic from Rwanda to South Africa. Here is how we do it. We go to IP VPN instance, and then it was AS100, and then the IPv4 family. Okay, So the option you're looking for here is the tunnel policy, in short. Well, there's a confusion in Huawei because up here, tunnel policy, you're able to say it in full, but inside the VPN instance, it's in short form, but it means the same. So the tunnel policy, now we reference that tunnel policy here, which is bind this one here. So that's the name of our tunnel policy. We say bind tunnel policy, then we commit. Now, if we configure something, if you configured everything correctly, which I can tell you we have not, because this one will fail, let's go back to our virtual private PC here and issue that traceroute. That's the traceroute command that we had issued earlier. Initially, that traceroute command was able to complete, as you can see from this output. So now let's give the same. Let's give the same, because now we are tracing our server in South Africa. Let's give the same command and see if it works. It doesn't. It does not work because it tells you clearly here the destination host is unreachable. The reason as to why this is failing is because for Huawei you have to let's go and display our interface tunnel 005. The reason as to why display current, sorry. The reason as to why it is failing is because in Huawei display. Okay, I'm sorry. The reason as to why it's failing because in Huawei you have to tell that tunnel that you have reserved it to be used for binding. As you can see, the tunnel policy we created before had a binding keyword, but if you go to our tunnel that we created, there is no binding keyword here. So you have to go inside this tunnel and say, we have reserved you to, we have explicitly told you, or we are explicitly telling you that, or we are binding you to be able to be used by our customer, in this case, which is AS100. So what we do is we go inside this interface and issue the keyword MPLS TE reserved for binding. Then you commit. This is your magic command right there. This will enable you now to be able to have this traceroute command complete. You go back and issue the same command. This time round it will complete. And if you can see, earlier on, what we were doing is we were going to 4 before we go to 5, as you can see there clearly. But now, after configuring the explicit path and clearly telling the customer which path they should be using, we are now going to 2. Sorry, we are now going to 2. It's failing me. Let me just use the normal word. We are going to 2 first, which is what we had said we are going to use. Remember, we said we are going to use this path. We're going to use this path here. Okay, down here, and then for the return traffic, it was supposed to use this part. Sometimes technology fails you in a ways you don't want to be failed. You're going to use this path, then come down here. Okay, so I hope you've been able to memorize that so that I can clear our screen and we go ahead with the configuration. So now we're going to 2, then we go to 3, then we come down to 5. So that this proves that our explicit path is working. This is for Huawei. How do we do the same for Cisco? This is our last path. How do you do the same for Cisco? For Cisco, again, you go now to, because now traffic was coming this other end. Now we want to traffic to come from this other end. Yes, Felix. The tunnel, the other name for tunnel is LSP. Because Felix is asking if I configured tunnel under one direction. Yes, the tunnel is configured to one direction because LSPs, as we said, are unidirectional, not bidirectional. Because traffic coming from Rwanda is using our tunnel, but traffic coming from South Africa to Rwanda is still using our the LSP that has been decided by our IAGP. Now that's what we want to go and change, because if you see, if you come to our server, if you're the trace route here, the trace route here is that you are supposed you're coming to PE05, then you use this device here, PE04, before going to Rwanda. Now we want to influence the traffic in a way that it will use the traffic coming from Rwanda. Sorry, traffic coming from South Africa will use this path. That's what we want to do now. That's what you want to do. Okay. So let's go ahead and do that. In South Africa, the command to do that, first of all, we have to define our explicit path by the command IP explicit path, give it a name. We can say to, maybe you can say path to CA09. CA09. Okay. And then the command in Huawei is next hop. In Cisco is next address. And then now you give the address, the IP address. So we're in South Africa, and we want you to go to using this red path here. So our next hop, our first next hop will be 20.1.45.4. Our other next hop will be 20.1.24.2. Our next hop again will be 10.12.1. Basically, what you are able to see on the screen using the red, this is red or is it purple, whatever that color is. Now, after configuring our explicit path, now we go ahead and configure our tunnel. So the command is interface tunnel. It's going to 1. So let's give it tunnel 100, for example. Okay. Now again, we want to tell this interface to use the IP address of, because we have to give it an IP address. But instead of configuring it manually, we want to tell this tunnel to use the IP address of our loopback interface, which in this case is 5.5.5.5. And how we do it is you come and do IP and numbered loopback 0. So that will tell it to use the IP address of our customer. And if you quickly verify, do show IP interface brief, you can see it has taken the IP address of our loopback interface, the same IP address. The next thing we need is the destination. So the destination for this particular tunnel will be 1.1.1. So we configure that as the destination. Now, those ones who have configured GRE, so this is different. So we have to tell this particular tunnel or explicitly say that this particular tunnel interface will be used for MPLS traffic engineering. And the keyword here, I think it's tunnel mode, if I'm not wrong. Yes, tunnel mode. Then you come and say MPLS traffic engineering. That's it. So we have now told that this this particular tunnel will be used for MPLS traffic engineering. Now, the next thing that we need what do we need? We need to explicitly say, let me see, let's see what we've done so far. Do show run interface tunnel 100. This is what we've configured so far. As you can see, it's not a lot. So we need to explicitly tell the customer, also this tunnel here, to use the path that we had configured. And what was our path? Our explicit path. Do show IP explicit path. This was our path, and this was our name. So we copy this name, give ourselves some space, and say MPLS traffic engineering. Now this is where No. So the keyword is tunnel, MPLS, traffic engineering, path option 1. And then you can either choose dynamic meaning the IGP will be able to define or pick a path for you, or you choose explicit path, which is what we want. So we say explicit, and then the name of our path was this guy. So currently our tunnel is down. So if that explicit path is valid, the moment we give this command here, the moment we give this command, this interface will automatically come up. So fingers crossed. Let's see. There you go. Our tunnel is up. Then it means our explicit path from South Africa to Rwanda is valid. And Cisco has a very good verification command for explicit path confirmation. The command is show MPLS traffic engineering tunnels, then that tunnel ID. It tells you clearly that admin wise the tunnel is up, operational wise it's also up, it's also valid, and the signaling is connected, meaning we are able to signal the other end of the tunnel, which is Rwanda PE01. Okay, and then down here, let me expand it. Down here, as you can see clearly, if I can use our pen, not sure where it has gone. Down here, as you can see clearly, you can be able to see our explicit path. It goes to 4, it goes to 2, and then it goes to 1. Again, for Cisco, it gives you an option of telling you, you know what, you've configured that as your tunnel, fine, no problem. But for us, the shortest and constrained, remember we said RSVP uses constrained shortest path algorithm, but the normal MPLS without traffic engineering does not use that. It uses unconstrained path. So Cisco will tell you, this is your explicit path, yes, but for us, the shortest unconstrained path is this. Okay, so you're able to, meaning if we would go ahead and configure dynamic instead of explicit path, if you'd use this particular route, which is what we saw before. So now, again, our tunnel interface is up. But as of now, if we go to our server and issue that traceroute command again, it is not using our tunnel. So we have to explicitly tell traffic to use that tunnel. And how do we do it? In Cisco, it's a very interesting way to configure it. So please pay attention kindly. So how we configure that is that, first of all, 3 things. We need to come up with a dummy static route. I'm using the word dummy because this particular interface is not configured anywhere, either on a loopback interface or a physical interface. So we need to tell our router to just configure a dummy IP, a dummy static route. Number 2, we need to configure an IP extended community list. I know it's a lot. And then number 3, we configure a route map. So that the route map is what will be able to enable us to influence traffic. I know that there's a way you can just simply go and do. Let me just show you that. Conft interface tunnel 100. So far, display run interface tunnel 100. So far, what we've configured. Now it's show, not display. This is Cisco. Do show run. What we've configured is this. Now, the easiest way to configure or the easiest way to tell this traffic to use this tunnel interface, the easiest way is to configure the command tunnel MPLS traffic engineering auto route announce. This is the easiest way because now your traffic should be able to use that tunnel. You see, Earlier it was going to 4, then it goes to 1, but now it goes to 4, then it goes to 2 before it goes to 1. This is the easiest way, but it does not work if at all you have multiple customers and you have to explicitly tell those customers which tunnel to use to route traffic from South Africa all the way to Rwanda. If you have one customer, that's good. It's fine, you can do it. But if you have many customers, this option might not be the best one. That's why I have decided not to use it. So we'll go back here and remove this command. After removing that command, we go back and confirm that our server is not using that particular tunnel. And it's not, because now it goes to 5, then it goes to 4, then it goes to 1. Earlier it was going to 2, where or what you want it to do. So let's go and configure an IP route, a static route. We just do a dummy IP and say IP route. It's a /32 IP route. We can pick any IP, but we prefer to have a private IP address because it's not routable. And then because we're configuring it within our MPLS backbone, then when we are doing advertisement of routes to the global routing table, because of our route maps or our route policies, we'll be able to filter out this particular private IP. That's why it's recommended to use a private IP. We can choose any. So let's use 172.16.1.1. Since we say it's a /32, so the subnet mask is 255.255.255.255. And then now we are able to have options, as you can see. The option here, you can give an IP address as the next hop, or you can give a tunnel interface. As the next hop. So in our case, we are going to use tunnel 100 as our next hop. So if we do that, if you say do show IP route, that interface, that particular static route is in your global routing table. Now, if you go to currently, this is what the output is unicast. Show it's do show BGP VPN before unicast all. So this is currently the next hop address for traffic under VRF S100 to go to 1. It has to go to this particular next hop, and if you trace that next hop, if you trace that particular next hop, it is using IGP, the shortest path. We don't want this behavior. We want to use the path that the customer is paying for, because they are paying us a lot of money for us to be able to give them that best path because of bandwidth, latency is lower, it's not degraded, So that's what we want. So we've configured the static route, number 1. Number 2, now we go and configure an extended community. Why we're doing extended is because under the route map, we want to go and match the route target. You remember we said the route target is what controls the import or export of customer routes. So we want to go and match that route target. And for us, do show run VRF, our route target is 2000 :100. That's our route target. So we want to go and match this route target and be able to tell this device here if the customer route matching this route target here wants to go to Rwanda PE01. Therefore, instead of using the IGP's defined path, I want that traffic to use the tunnel that we have defined. So let's go ahead and create, because the route target is an extended community attribute, so we just have to match it as an extended community list. So we define an extended community list. The option here, you can use numbered or standard. Let's just do standard because it's a simple one, and then give it a name. a name that you can be able to know what you're talking about. So let's just say S100 extended community, for example. And then after that, we now permit, what are the options we have? Route target extended. We permit the route target. Permit route target, and what is our route target? 2100. That's it. If you give the command do show IP extended community, this is what we have. So now we have an extended community. We are permitting this route target. So we need a route policy for us to be able to match this route target, and after matching, sorry, for us to be able to match this community list, and after matching that community list, we can now go ahead and influence the next hop behavior. Instead of it using 1.1, I want you to pay attention. Let me just grab this one here. I want to grab this and put it to our notepad. Okay. Now, so we have to go and create a route map. So route map, give it again a name. So S100 route map. Route map. That's the name we're giving it. Okay. Now we want to match our IP. No, sorry, not IP. You match extended. Match extended. Jesus. Match extended community. Now the name that we had given our extended community was this one here. So you're telling this route map or route policy in Huawei and Cisco XR. You're telling this route map that if you match this extended community, which had this route target, okay, therefore set IP next hop. And what is our next hop? That set IP next hop. Our next hop was that default IP route that we configured, which was 172.16.1.1. Okay, and then this route map has an implicit deny. You go ahead and just configure a route map to allow anything route map. Then I think this is supposed to be. We can give it 20, and then we allow everything else. So if you see what we've done, do show route map. We have a route map called S100 route map. We are matching our extended community list, which in this case is S100 extended community list, and then we are saying if we match this particular community list, then we set our IP next hop to be 172.16.1.1, and then anything else that is not matched should just be allowed. Permit anything else that is not matched, because route maps, just like access lists, have implicit deny at the end. Okay, so that's it. No, it's not. Lastly, remember when we are in Rwanda, if we can say display current VPN instance, we were able to tie this tunnel policy under our customer instance or VRF. The same thing is to happen in Cisco. The way you do it in Cisco is a bit different. So you go inside our customer VRF. In this case, we have do show run VRF. So we go inside our customer VRF, which is S100. So we say VRF definition S100 under our address family IPv4 unicast. Under this family, what we are looking for, the options we are looking for here are now we have to import. We have to import that particular route map that we defined. Remember the route map that we defined here, this route map called S100 route map. We have to import this route map. So say import keyword, and then map keyword again, and then now you're able to give your VRF import route map. So it clearly tells you give a route map name, this particular thing. So our route map name was AS100 route. That's it. We are done. So what is done is just what is left is just to do verification. So we can show run. Let's see what we have under our VRF. So what we have under our VRF is that we have a route target, route distinguisher, and we have imported our route map, which basically, remember the work of our route map was to enable us change the next hop behavior. Okay, so our route map is enabling us to change the next hop behavior. So when we did show BGP VPN before unicast all for traffic to let me minimize this. When we did show BGP VPN before unicast all for traffic that was going to Rwanda, that is this device here, sorry, this prefix here, and this prefix here, and this other prefix. They were using 1.1.1.1 as the next hop, and as we saw clearly, for you to go to, you can just confirm it. For you to go to 1.1.1.1, we are using IGP. But now with our route map, with the configuration that we've been able to do, we have been able to influence that behavior. So let's go and say show BGP VPN before unicast all, and see what we are doing here. We're dealing with here. Now look at this. Let me bring it here. Here we had 1.1.1.1 as the next hop. But now after the route map configuration, we are getting to have 172.16.1 as the next hop. And if you recall correctly, show run begin IP route. If we recall correctly, we were able to define here. If we recall correctly, we were able to define or configure a static route. And what we said is, for any traffic that is coming to that has a next hop, for any traffic that has a next hop as 172.16.1.1, then use the tunnel interface, this tunnel here. And this tunnel interface, show run interface that, and this tunnel interface, as you can see, we have been able to tell is, well, for you to go to 1.1.1, use this explicit path. And what does that explicit path say? Our explicit path says, well, for me, traffic from South Africa to Rwanda, I have to go to 4, then go to 2, then come to 1. That is exactly what we now want to do. So let's go back and do a trace from our server. Earlier on, the last one you did without the configurations of the route map, it was going to 4, yes, but it was going to stretch to 1 instead of going to 2. But now, if we do this, you can clearly see now we are going to 4 and we are going to 2 before going to 1. So traffic is using the path that we have been able to define. And that right there, guys, is how we configure MPLS traffic engineering and be able to influence traffic or how traffic flows within your MPLS infrastructure. That was quite a lot.
Thanks, David.
Any questions? You're welcome, Martin. Any questions? Any questions now that we've done this configuration and it's done? Hold on, guys. Lastly, Martin, before questions, let's assume for some reason, this particular path here is congested, But remember, the customer is only paying for the best one. So this path is congested, and we want to give our customer the best experience that there is. Now, since this is congested, we can say, okay, as we wait for this, there's a way you can do it dynamically, but I don't want to do it right now. As we wait for this traffic, as we wait for this path to be optimized, what we can do is we can give this customer, you can configure this customer to use this particular path, the yellow one, and that is simply done under the explicit path. So if you say do show IP explicit path, this is what we have. It goes to 4. So currently it is using the red route, or the pink one. I think this is pink. It's using the pink route, but now the pink route has a problem. Customer is complaining. So we've determined where the problem is. So we can simply reroute traffic to use the yellow route. This is how we do it. Under our explicit path, you go and say IP explicit path. The name is that. Now we had 4, so we want to change this behavior and configure it to use the yellow route. So what we do is we can say no index 1. That removes that one. So no index 2, no index 3. So that our explicit path is actually explicit path. Our explicit path is now blank. So we configure again. So the next address will be 20.1.35, and you see our tunnel has gone down since we've removed the explicit path. So .3, and then we want it to come down to 20.1, 34.4, and then we want it to go to 20.14.1. Now our tunnel interface comes up because again that particular path is valid. Okay, and then we say that's fine. Let's save this. So we come and confirm and tell the customer, you know what? We have seen where the problem is, but traffic has been moved to a healthy path that is stable and optimal. Kindly test. The customer tests. There you go. Now we are going to 5, then we go to 3, then we go to 4. Sorry, we go to 4, and then we go to 1. That's how you are able to reroute traffic for the customer. Guys, I think I'm done talking for now. Let me just take a breather for like 2 minutes as you ask questions. There's a question that was asked by a gentleman regarding do I see MPLS being replaced by SD1 in the next 10 years? I think no, because there are things that MPLS offer you that SD1 does not offer you. For example, based on the basic knowledge you know about SD1, I don't think you're going to be able to do explicit paths. Maybe Martin can. That's why I wanted Martin to answer that question, because he's actually dealing with SD1 on a daily basis. So Martin, please feel free to come in and answer our.
Yes, David. I'm gonna sign you up as my provider now. Okay, to answer the question, yes and no. So yes, because MPLS is very expensive, whereby SD-WAN gives you flexibility to use any link that you want. No, because when you use the internet, the internet will not give you prioritized services. Like if, let's say, you have voice as an example. So whereby with the MPLS, you can have, let's say, a low bandwidth, and on the SD-WAN, there is a similar policy that behaves just like the explicit path in the SD-WAN. So that explicit path you can match based on application tags, source IPs, destination IPs, and then you can then point that traffic over the MPLS link. Does that answer the question? Is Tepo still in the call?
Yes.
I'm waiting for him to confirm. Okay. Right, so we are good with that SD1 question. There's another question here. I think Felix, I answered you. You had asked if you just configured a T tunnel only in one direction. Yeah, tunnel or LSPs are unidirectional. You configure them just one direction, but just to ensure that you have your customers are using the optimal path, then it's ideal if you configure a tunnel from, for example, in this case, Rwanda PE to South Africa PE, then the reverse traffic also, it's also ideal to configure an explicit tunnel. So it's not bi-directional, it's unidirectional. So I think I answered that. And then your question was again, what happens when the service? What happens with the service if one device that belongs to the explicit path goes down? So Felix, it depends. It depends. I was avoiding to do it, but now let me just go and do it. It depends. So our tunnel 100 here, for example, show run section router show run interface tunnel 100. So Felix, it depends. What is the customer paying for? If the customer has paid for just one explicit route, there's no redundancy. Then if by bad luck, and of course it happens, if there's an outage, for example, if there's an outage within this route here, then the customer has to wait for that outage to be resolved. Unfortunately, that's the contract. But if the customer has paid for redundancy, then it means automatically we can reroute traffic for this customer. We can either configure an explicit route or give them a dynamic route, which means now if your explicit route goes down, you can use the next any available path to your destination. So for Cisco, what you do is where you configured MPLS engineering path option 1, we can go ahead and configure the same thing here and say path option 1, but in this case we say dynamic. If we had another explicit path, we would use it. So we say dynamic. Okay, and then you go and configure this interface here, this tunnel here, tunnel MPLS engineering, to do what we call fast reroute. Okay, I forgot to record label. It's good to record labels here. Fast reroute. So do show run interface tunnel 100. So this particular no, I messed up, guys. Sorry. This is what I wanted to issue. I wanted to issue this, and then now the other one should be 2, not 1, dynamic, so that you have 2 explicit routes. We have 2 routes now. The first one here is the one that the customer has paid for because it has lower latency and it's optimized and everything is fine, no complaints. The other one here is what will enable the customer to automatically use any next or any available route from South Africa to Rwanda. So currently traffic is going via the express route, as you can see. Let's go ahead and shut down this interface in Kenya P03. And the interface is interface Ethernet 102. Let's shut down this interface. Before shutting down that interface, let's go and do a ping. Does this thing have a way of counting? Yeah, it has counting. Ping, you count, let's count 1,000 times. No, sometimes these things will fail you. Jesus Christ. I think you ping the IP address, then you count 1,000 times. Thank you. So let's go and shut down this interface in Kenya P. This interface because it's used within our, or better still for you. We can go ahead and okay. I don't want to shut it down because it will take time to come up. Let me just shut this interface here, and then commit. Let's go and see the behavior. So we have timeouts. We have timeouts because we've not enabled node and link protection, so it will take time before the explicit path can kick the what is it called? It will take time before traffic can be routed. But there's a way you can configure this to take effect immediately. So this will take time. It's really taking time. That we don't have, and this kind of behavior, when you're dealing with critical environments, it can bring you problems. So it's taking time to reroute. But just to answer you, that's how you can deal with it, Martin.
Yeah, and I think what I just showed there stipulates the reasoning of why or why MPLS is important. So what you showed there is the SLA. So with internet links, you won't have those things because it's best effort. So if there's an outage, they say, "Oh, go fly a kite." Wait for the link to come up because that's what you're paying for. So that's why I would say MPLS is not going away anytime soon because of these reasons.
Yeah. Okay. Felix, I wanted to answer you, but it looks like something is failing me here. So MPLS, traffic engineering, tunnel 100. It's using it clearly says. I think these devices here can also mess you up. It is not working, guys. It's not working. Let's see. That's interesting. Well, do we have time to troubleshoot this? Because clearly this has been used as the next hop, so the path, and everything is working correctly. I am not quite sure why we can't do the pin.
It's okay. I feel the explanation was clear. Maybe we can just pick a few more other questions. We already almost at 6.
Yeah, it's getting a little late, but basically, Felix, from the explanation, you can be able to configure redundancy for the customer. To answer your question, so if that node goes down, then the customer will use the other route.
Lisa?
Yes, please bear with me.
Yes.
To hear some noise on the ground, but my question is just a very quick one. You see, as a network engineer, how will you be able? How can I be able to select or to choose a good path for a customer in any case on the MPLS network?
Sorry, Lisa, I can't hear you.
Elisa, maybe you can type your question on the chat. We can't hear you clearly.
Okay, no problem. No problem.
David, there was a mention on the chat that the reverse path may not be working, which you may also need to test because, yes, you've configured a dynamic path on one side, but the other side, will it be able to switch?
Which other side?
You are pinging from the server towards that is C09, right?
Yeah.
And the dynamic path you configured it, was it on which node? This was in South Africa PE05, right?
Okay. You see, what should guide you here is this particular output here, because clearly it was able to pick this, and then down here it told us that it was using this route, and we just saw it a few minutes ago. It's working. So currently, we've gone back to our explicit route. I mean, maybe it's something I need to explore and see why it was not able to automatically switch. Okay?
And what if you check the status of the tunnel from the other side of the connection? Because
it is unidirectional. Then it doesn't matter if that tunnel is down or not on the other end.
Yeah, but for the ping, you still need a reply from the other side,
which is working. It's okay.
okay, we can let's answer questions, and then I feel that was from Oscar actually. Ali.
Hello, can you hear me, guys?
Yes.
Okay, I have no questions, but I couldn't pass the opportunity to thank David for his trouble and this enormous task of explaining all the subjects that he mentioned in this video. It's an enormous task, and I appreciate his efforts. And I can't believe that someone could do this work in such an amount of time. It's phenomenal, and I thank you very much on behalf of all the team. Thank you very much. It's been like I'm bedazzled halfway through the lab as to the patience that he had and the amount of patience he had to relay all this information. And I wish you the best of luck and thank you very much.
Thanks, Ali. I really appreciate it. Thank you so much.
Thanks, Ali. The question from Elise is he's asking, as a network engineer, how will he be able to choose a path for any customer who wants to use their MPLS network?
How will he be able to choose a path for any customer who wants to use? Okay, Elise, there's quite a lot. That not a lot, but there are things that the customer will come and ask you. For example, what latency are you offering them from Rwanda to South Africa and vice versa, for example? Because for them, maybe they want. If you go back to your QoS training or your QoS concept, traffic like voice traffic, for example, I think if I can remember correctly, it requires about is it a latency of below 40 milliseconds? It requires a latency of below 40 milliseconds. Nowadays with the fintech companies coming in, they require traffic. They require latency, very low latency. That's number one. So how to determine that is number one, latency. What does the customer want in terms of latency? Number two, bandwidth. What is the customer bandwidth requirement? Okay, and of course, number three, cost. This is the most obvious one. So the two ones will define the two reasons will, number one, latency and bandwidth. Those ones would and then there's also the degradation, or how stable is this route, because having an MPLS infrastructure like we have here in Africa, for example, this is Rwanda, Uganda, Tanzania, Kenya, and South Africa. We could be having countries whereby our routes are passing through areas where the host government has decided to do construction, for example, or that area is prone to either conflict or a lot of sabotage or tampering or vandalism. So again, that should come to mind when you're discussing with the customer. And remember, Elise, it is not you to decide which path the customer is supposed to use. It is the customer to decide. Your work is to configure and deliver the customer what they want. So the most obvious ones are latency, the bandwidth the customer's bandwidth requirement, and also how stable is that particular path. Just tell them this one is not very stable. It could be bandwidth latency is less. It meets the bandwidth requirement, but it's not stable. Then that's something you should tell the customer and tell them we can give you this as the primary path, but to be safe, because of your services, we can also give you this as the secondary route at a discounted at a discounted fee. So basically, those are the things that will be able to help you to configure be able to choose which path traffic is using to and from the customer.
Thank you, Brother David. Thank you.
You're welcome.
Last question
All right.
from the
Yeah.
team. If there is any other question, any burning question from the team, you can raise up your hand and ask your question.
Yeah, hello, Martin. I
Yes.
joined the lecture very late, but I don't know when this section will be posted on YouTube for us to, go and rewatch.
It will be posted hopefully today in the evening, later in the evening, before close of the day.
Okay, thank you.
Yeah, I'll upload it immediately. Olayemi?
Okay, good day,
Thank you, Brother
everyone.
Martin.
Thank you, everybody. Thank you, Martins and David, for this presentation. So my question is, I think I've seen one scenario where you use VRF or VPN instance without MPLS. I want just to have an understanding why we want to use MPLS on a network without VPN instance. I think I saw one time like a inter-VPN static route being used in a particular environment. Do you understand my question? MPLS without VRF. I mean, VRF without MPLS.
David? Hi, David. David has dropped or is still on the call?
I think maybe, yeah, there we
Sorry, I was on mute.
Oh.
Sorry, I was on mute. No, speaking. Can you hear?
Yes, we can hear you.
So Olayemi, you wanted to know because VRF without MPLS, why that is the case, right? If I got
Yes.
you correctly. Okay. So first of all, let's go back to the basics and answer the question: what is the work of the VRF? Basically, a VRF enables you as a service provider to be able to use your one device, for example. For example, this PE. My pen is failing me, and I don't know why it's failing me. It was not failing me before, but now it's really failing me. Anyway, so let's take this device as an example. Okay, so you have 2-3 customers here who want to communicate to each other. Two customers here, and then you have so assume this is company B, this is company B, this is company A, this is company A. They want to use this one PE device here to communicate. Now, how to ensure that their routes are isolated? That's where your VRF comes in. It has nothing. It doesn't really mean that you have to use MPLS for VRS. No. we could decide and say we're not doing MPLS, then let's just do normal routing. We still need VRFs just to ensure that the customer routes are isolated. So VRFs is simply to give you um, uh, privacy or route independency to make sure that various customer routes are isolated. It does not really mean you have to use it with MPLS. You only come to use MPLS with VRF when you're configuring L3 VPN, because when you're configuring L2 VPN, as we saw, they're not VRF. For L2 VPN, we didn't configure any VRF when we're doing the PRF. So that's why we can have a VRF without MPLS, but you most common application of VRF, you'll find it in L3 VPN configurations.
Thank you very much.
You're welcome.
I believe
It's been 3 hours.
we've exhausted the questions, and again, we appreciate you, David, for the session. It has been a very informative session. Time will never be enough again, but we keep trying and
Yeah.
covering these sessions in the available time slots. So we appreciate your effort and time in preparing through the session, and also everyone who has joined the session. The recording will be uploaded today, as I've mentioned before, so that you can review it and also do the labs on your own. If you meet any challenges while you are doing the lab, we are available on the platform. You can always ask your questions on the WhatsApp chat, and then we will be able to respond to them. Anyone with anything to mention? David, you have anything to? You have any closing remarks for us?
Yeah. You see, this forum or this session would not have been a success without you guys. So first of all, thanks to Martin for giving me the platform to showcase or to be able to share knowledge. Because in the course of 2 weeks, when I was doing the preparation for last weekend and this weekend, there's a lot that I myself have been able to learn actually. I've been able to, I can see, polish or furnish my skills in MPLS, which has also really helped me. So thank you for the platform, and then for the audience, the community guys, my fellow, I can say, colleagues, because we're in the same community and in the same group. Thank you so much for the trust, because you trusted that I could deliver this. You created time to be here. I know it's a weekend, you should be having time with your family, but you decided to be here. I really appreciate it so much. Let's keep engaging. Let's keep sharing knowledge. Hopefully, I will come back. I have been very fortunate, by God's grace. I have done 2 consecutive sessions. So I think that is something that I'm very grateful, and it's because of you guys that is happening. So maybe one day, in the near future, I'll be able to come back with another topic that might be interesting to you guys. Other than that, even without these sessions, let's engage. Let's keep engaging. If you have an issue, if you want to learn, if you want to share something, just feel free to reach out. The good thing is, um, I don't think there is someone who is an expert in anything to say, because we all learn, even the experts all learn. So let's learn from each other. And again, I can't thank you enough for getting time to be here, because imagine if you're not here, I will be speaking to myself with with Martin. But you were here. You've been patient since 2 p.m. Kenyan time. We've covered a lot of content. It's been 3 hours. So thank you so much, guys, and hope to come back again and take you through something else.
Thank you. We are also again very grateful, and we still welcome you back with any other topic that you feel you can share. And any other guy who feel that they have something to share with the team on the platform, they are also welcome to come in and share their knowledge. Guys, we learn by sharing what we know. You challenge yourself. It takes time to prepare for these sessions, and when you are preparing for them, there is a lot that you yourself learn and also practice. So it's always good to share the knowledge, and that's why we have this platform. So let's keep that spirit. Let's keep sharing the knowledge and empowering each other through the platform. Anyone else? Elise, I see your hand raised up.
Yes, Brother Martin, I wanted just to say, even if you can't hear me properly, I just want to say thank you so much, Brother David, and also to you, Brother Martin, all the works that you are doing for us. Thank you.
You're welcome, Elise. Anyone else before we close? Okay, then let's clap for David. Let's clap for David for such amazing session. And I hope you guys will have an amazing weekend, and we will communicate when we'll be having our next session in the near future. Thank you so much for joining again, and see you in our next session.
Thanks, Martin. From Kenya, we say Koheri.
Thank you.
Goodbye. See you
Thank
soon.
you. See you.